to sleepy facts with Justin. Tonight, we are going somewhere very few human beings have ever been. We are going down, slowly, gently, through layer after quiet layer of the world's ocean, into the deep, far below the surface of the sea, where sunlight fades to a thin and watery blue, and then to nothing at all, where the water grows cold and still, where the pressure is immense and the world is very, very quiet. There is no rush tonight. There is nowhere else you need to be. You are already exactly where you are meant to be, warm and still. And all you need to do is breathe and listen, and let the deep ocean carry you gently towards sleep. The ocean is one of the most remarkable places on our planet. It covers more than 70% of the Earth's surface. It holds more than 96% of all the water on Earth. It is so vast and so deep that even today, with all of our technology and all of our curiosity, most of it remains unexplored. More of the seafloor has been mapped on other planets and moons than beneath our own ocean. There are places at the bottom of the sea that no human eye has ever seen, and no machine has ever touched. That thought is not alarming. It is wonderful. It means that the deep ocean is one of the last great frontiers of discovery on our world, a place full of possibility, full of quietly living creatures, full of ancient, slow processes that have shaped this planet for billions of years. Tonight, we are going to drift through that world together, not rushing, not startling, just drifting. Imagine standing at the edge of the sea on a calm and quiet night. The water is dark. The surface catches just the faintest shimmer of starlight. There is a soft sound of small waves moving against the shore, a gentle rushing and retreating over and over like a slow breath. The air smells of salt and coolness. The horizon is invisible. The water and the sky seem to merge into one long, soft darkness. Now imagine stepping off the edge and not falling, but sinking very slowly, as though you are a leaf settling through still air, down through the surface, down through the warm upper layers of the sea. The light above you shifts from gold to green to the palest blue. The sounds of the surface world fade, and below you the ocean opens up, deep and dark, and full of a silence that is so complete it feels almost like a sound of its own. That is where we are going tonight. The deep ocean begins at a depth of around 200 meters below the surface. Scientists call this the boundary of the sunlit zone, the place where light from the sky above finally loses its strength and cannot reach any further. Below 200 meters, the world of the ocean changes completely. Temperature drops, pressure rises, darkness gathers, and life continues. Life, as it always does, continues. This is one of the most important things to understand about the deep ocean. For a very long time, scientists believed that the deep sea was a desert, that the cold and the darkness and the crushing pressure would make it impossible for any living thing to survive down there. That belief turned out to be completely wrong. The deep ocean is alive with creatures, strange creatures, soft creatures, slow creatures, ancient creatures. Some of them are so well adapted to life in the dark that they carry their own light with them. Some of them are so patient that they barely move at all and simply wait in the quiet while food drifts gently down to them from above. Tonight, we will learn about all of these things, about the layers of the ocean and how they differ, about the cold, deep currents that carry heat and oxygen around the whole planet, about the remarkable animals that live in absolute darkness, about the seafloor, which is not flat and featureless as people once imagined, but a dramatic, mountain-strewn, canyon-carved landscape as varied as any continent, about the strange places where hot water pours from cracks in the earth's crust, and entire communities of life have built themselves around heat rather than sunlight, about the ways scientists explore these extraordinary depths slowly and carefully, using machines built to withstand pressures that would crush a human being in seconds. But we will learn all of these things slowly. There is no hurry here. The deep ocean operates on a different time scale to the one we live in. Things happen slowly down there, Water moves in great, slow rivers that take hundreds of years to travel from one part of the ocean to another. Animals live long lives in the cold and quiet, growing slowly, reproducing rarely, drifting through decades and centuries in the dark. Some creatures of the deep sea are believed to live for hundreds of years without ever seeing sunlight. There is something deeply reassuring about that, about the idea of a world that moves at such a gentle pace, a world where nothing rushes, where the darkness is not frightening, but simply the natural condition of a life lived far from the noise and the brightness of the surface. So settle in. Let your body grow heavy. Let your shoulders drop and your hands rest open at your sides. You do not need to follow every word tonight. You do not need to remember any of this. You can simply let the words wash over you, like warm water moving around you in the dark, and drift. We are going down now, very slowly, into the deep ocean, into one of the quietest, most ancient, most mysterious places on our planet. And as we go, we will let the weight of all that water above us become a comfort, a gentle pressure, holding us still while the world of the deep unfolds all around us. The water is very deep here, and it is very calm, and so are you. The ocean has many layers. If you have ever stood at the edge of the sea on a bright summer afternoon and looked down into the water, you will have noticed the way the light plays through it. Near the surface, everything is bright and shifting. Sunlight breaks into long, pale shafts that move slowly as the waves ripple above. You can see the sandy bottom in shallow water, lit up gold and white. You can see small fish darting through the light. Everything near the surface feels alive with brightness. But sunlight does not travel forever through water. Water absorbs light. It takes it in, little by little, with every meter of depth. The very first few meters of ocean absorb more than half of the sunlight that enters. By the time you have descended to 100 meters below the surface, only about 1% of the original sunlight remains. The ocean at 100 meters is dim and blue and growing cooler. And by the time you reach 200 meters, even that last small fraction of light is gone. 200 meters. That is where the deep ocean begins. 200 meters is roughly the height of a 60-story building. It does not sound like a great distance when you think of it that way. And yet, the journey from the bright surface down to 200 meters is one of the most dramatic transitions in the natural world. In those 200 meters, the temperature drops, the pressure increases, the color of the world shifts from warm gold and green to cold, deep blue, and then to nothing at all. Scientists call the uppermost layer of the ocean the sunlit zone, or the euphotic zone. This is the world that most of us know. The sunlit zone reaches from the surface down to around 200 meters, and it is the layer where life is most abundant, most visible, and most familiar. This is where coral reefs grow, fed by the warm light from above. This is where great schools of silver fish move in slow, turning clouds. This is where dolphins play in the bow waves of ships, and where seabirds dive from above to snatch their meals. The sunlit zone is where the ocean meets the sky, and where the energy of the sun powers almost everything that lives. But the sunlit zone is actually quite thin. The ocean has an average depth of around 3,700 meters. The sunlit zone at 200 meters represents only a tiny fraction of that vast depth. Imagine the whole ocean as a tall building with 100 floors. The sunlit zone would be only the top 5 or 6 floors. Everything below that, floor after floor after floor, stretching down into the dark, is the deep ocean. And the deep ocean is enormous. More than 95% of the living space on our planet is found in the deep ocean, not on land, not in the shallow seas, not in the rivers or the lakes or the forests or the plains. Down there in the cold and the dark, below where light can reach. The deep ocean is the largest living space on Earth, and for most of human history, we knew almost nothing about it. Below the sunlit zone, the ocean is divided into several more layers, each deeper and darker, and more extreme than the last. The first of these is the twilight zone, which scientists call the mesopelagic zone. It runs from 200 meters down to about 1,000 meters below the surface. In the upper reaches of the twilight zone, there is still the very faintest trace of light. Not enough for plants to grow, not enough to read by, but just enough that some animals can detect it, just enough to cast the very palest shadow. The twilight zone is a world of deep blue and purple shadows. It is cold, typically between 5 and 15 degrees Celsius, depending on where in the world you are. The pressure at 1,000 meters is about 100 times the pressure at the surface. Animals that live in the twilight zone have evolved extraordinary adaptations to survive in this world of fading light and growing pressure. Many of them have huge eyes designed to catch every last scrap of dim light. Some of them migrate upward every night to feed in the sunlit zone, then sink back down into the twilight when dawn comes, hiding from predators in the deeper dark. Recent research has suggested that the twilight zone may contain more fish than all the rest of the ocean combined. That is a remarkable thought. A whole world of fish living in the dim blue shadows between 200 and 1,000 meters, quietly going about their lives far below the reach of sunlight. We have barely begun to understand this world. Below the twilight zone, the light disappears entirely. At 1,000 meters, you enter the midnight zone. Scientists call this the bathypelagic zone. From here down to about 4,000 meters, there is no light at all from the surface. None. The darkness is complete. It is the kind of darkness that is difficult to imagine if you have only ever experienced ordinary nighttime darkness. The kind where your eyes slowly adjust and you begin to make out shapes. In the midnight zone, there is nothing for your eyes to adjust to. There are no shapes. There is only darkness and cold and the immense, quiet weight of all the water above. But still, there is life. Below the midnight zone lies the abyssal zone, stretching from 4,000 meters down to around 6,000 meters. This is the world of the deep ocean floor. In most places, great flat plains of soft sediment, stretching for thousands of kilometers in every direction, covered in a fine, slow-settled dust of organic material that has drifted down from the world above. The temperature in the abyssal zone hovers just above freezing, typically around 2 to 3 degrees Celsius. The pressure is so extreme that it would crush a human body in an instant, and yet even here, in the coldest and darkest and most pressurized parts of the ocean, creatures live. They move slowly through the sediment. They drift through the water. They wait with great patience for food to come to them, and deeper still, below the abyssal zone, the ocean descends into the trenches. These are the deepest places on Earth, long, narrow valleys in the seafloor where the ocean floor has been pulled downward by the movement of the great rocky plates that make up our planet's crust. The deepest of all these trenches is the Mariana Trench in the western Pacific Ocean, where the seafloor descends to a depth of nearly 11,000 meters. That is nearly 11 kilometers straight down. The deepest point in the Mariana Trench is called Challenger Deep, and it sits so far below the surface that if you were to lower the tallest mountain on land, Mount Everest, straight down into it, the mountain's peak would still be more than 2 kilometers beneath the waves. Even Challenger Deep is not empty. Scientists have found living things even there, at the very deepest point on Earth. Small, soft, strange organisms adapted to pressures that defy imagination, quietly existing at the bottom of the world. When you think about the ocean this way, as layer upon layer upon layer, each one darker and colder and more pressurized than the last, each one still somehow alive, it becomes clear why scientists find it so endlessly fascinating, and why, despite centuries of exploration, we are still only just beginning to understand what is down there. But understanding is not what tonight is about. Tonight is about drifting, about letting the weight of all that water settle around you, layer by layer, quieter and cooler and darker, until the surface world is very far away, and you are resting in the still, soft dark of the deep, ocean is very deep and you are very comfortable. And there is nothing you need to do right now except breathe slowly and rest and let the quiet of the deep surround you. Close your eyes if they are not already closed. Imagine the color blue, not a sharp or bright blue, not the blue of a summer sky at noon, but a deep, soft, shifting blue. The kind of blue that seems to breathe, the kind of blue that moves very slowly. Now imagine that blue growing darker and deeper and quieter the further down you go. That is the color of the ocean as the light begins to leave it. That is what we are going to follow tonight. Gently, all the way down into the dark. Light is a remarkable thing. It travels across millions of kilometers of empty space from the sun to our planet in just 8 minutes, moving faster than anything else in the universe, and yet when it meets the ocean, it slows and bends and fades. Water absorbs light. It pulls it in, takes its energy, and lets it go as warmth. And because different colors of light carry different amounts of energy, they are absorbed at different depths, one by one, like notes in a slow and fading melody. The first colors to disappear are the warm ones. Red light is the lowest energy color in the visible spectrum. It is absorbed by water very quickly. By the time you have descended just a few meters below the surface, the red light is already gone, not dimmed. Gone. If you were to take a red object down with you and you looked at it at a depth of 10 meters, it would no longer appear red. It would look dark brown. At 20 meters, it would appear almost black. Red simply vanishes in water, absorbed in the uppermost layers before it has a chance to travel any further. Orange follows soon after. By 30 or 40 meters below the surface, orange light has been absorbed as well. Then yellow fades. Then green. Each warm color disappearing in turn, as though someone were slowly turning down the lights on the warmer, softer end of the spectrum. What is left is blue. Blue light carries more energy than red, more than orange, more than yellow or green. And so blue light travels deeper. In clear ocean water, blue light can penetrate to around even a little further under ideal conditions. This is why the deep ocean appears blue to those who dive into it. Not because the water itself is blue in the way that paint is blue, but because blue is the last color standing, the only wavelength of light that still has enough energy to reach those depths. As you descend, the blue deepens. Near the surface, it is bright and turquoise, alive with sparkle. At 50 meters, it is rich and true, a pure, deep blue that painters have tried to capture for centuries. At 100 meters, it is darker, more violet, the kind of blue that makes you feel very small and very still. At 150 meters, it is barely there, a faint cold glow that seems to come from everywhere and nowhere at once, and then it is gone. At around 200 meters, even the last traces of blue light have been absorbed. The ocean below 200 meters exists in a darkness that has never known sunlight, not in the way a cave is dark, not in the way a room is dark when you turn off the lights. The darkness of the deep ocean is absolute. It is the darkness of a world where light has never reached, where there is nothing to see and nothing to illuminate. And yet, even in this complete absence of light from the sun, the deep ocean is not entirely dark. Because the animals that live here have learned to make their own light, scientists estimate that around 76% of all animals living in the open ocean are capable of bioluminescence. That is an extraordinary number. More than 3/4 of all ocean animals can produce their own cold, living light through chemical reactions taking place inside their bodies. In the deep ocean below the reach of sunlight, bioluminescence is not a curiosity or a party trick. It is one of the most important and widely used tools for survival. The chemical reaction behind bioluminescence is elegant in its simplicity. Inside the bodies of these animals, a molecule called luciferin reacts with an enzyme called luciferase. The reaction releases energy, and that energy takes the form of light. A cold light, a soft light, a light that carries almost no heat. Just a gentle, quiet glow. The colors that deep-sea animals produce with this living chemistry are mostly blue and green. This is not a coincidence. Blue and green light travels furthest through water. In the deep ocean, an animal that produces blue bioluminescent light can be seen from a much greater distance than one that produces red or orange. Evolution, over millions of years, has tuned these living lanterns to the wavelengths that carry best through the dark water. And so the deep ocean, though starless and sunless, is not entirely dark. It flickers. It pulses. It glows in small, cold points of light, here and there, scattered through the black water like distant stars seen through a very long telescope. A jellyfish drifting downward, trailing a faint blue shimmer from the edges of its bell. A small shrimp, disturbed by some movement nearby, releasing a brief cloud of glowing particles to confuse whatever startled it. A lanternfish, rising toward the surface in the evening, its rows of small photophores lit along its sides like the portholes of a tiny vessel moving through a dark sea. The twilight zone, that layer between 200 and 1,000 meters, is where the transition from sunlit to lightless world takes place. And it is a transition full of strangeness and beauty. In the upper twilight zone, there is still just enough surface light to cast a very faint, diffuse glow through the water. Animals in this zone have to manage two very different sources of light. The dim blue-gray glow filtering down from above, which at certain times of day and in certain clear waters can still be just barely detectable, and the flashes and glimmers of bioluminescence produced by the animals around them. Many animals in the twilight zone have evolved eyes of extraordinary sensitivity to cope with these conditions. Some deep-sea fish have eyes 10 to 100 times more sensitive to light than human eyes. They are not larger eyes necessarily, though some deep-sea creatures do have very large eyes indeed. They are more efficient eyes, packed with more of the light-detecting cells called rods, tuned to the faintest possible signal, capable of detecting a single photon of light in an otherwise total darkness. Other animals in the twilight zone taken a different approach entirely. Rather than developing better eyes, they have abandoned eyes altogether. Some deep-sea creatures have no eyes at all. They navigate their world by pressure, by vibration, by the chemical traces of food or predators dissolved in the water around them. For these animals, light is irrelevant. The ocean speaks to them in other languages. The relationship between color and survival in the deep ocean is a beautiful and subtle one. Near the surface, color matters for blending into bright, varied environments. In the sunlit zone, fish are often silver, reflecting light in all directions, so they become hard to track. Coral reef fish are strikingly colored, using vivid hues to communicate with one another. But in the twilight zone and below, the rules change completely. Red is the color of invisibility in the deep ocean. Because red light disappears within the uppermost meters of water, there is no red light left at depth to reflect off a red-colored animal. A red creature at 500 meters appears completely black to any animal trying to see it. Black against black. Invisible. Many deep-sea shrimps, prawns, and fish are a deep, vivid red precisely because of this optical trick. Their redness is their camouflage. Their warmth of color becomes, in the cold and lightless deep, a perfect cloak. Transparency is another strategy. Some animals of the twilight zone are almost completely see-through. Their bodies, their tissues, even their organs are so transparent that light passes straight through them. A transparent animal in dimly lit water has no shadow, no outline, no presence that a predator's eye can lock onto. It is simply there, and not there at the same time. A ghost of an animal drifting through the blue. It is remarkable to consider that all of these extraordinary adaptations, the huge sensitive eyes, the bioluminescent lanterns, the red cloaks of invisibility, the transparent bodies, all of them have been shaped by light, by the presence of it near the surface and the absence of it below, by the way water strips color from the spectrum one wavelength at a time, until only darkness remains. Light gives the deep ocean its structure. The fading of light creates the layers, and the layers shape every living thing that dwells within them. And now the light is very nearly gone. We are approaching 1,000 meters. Below us, the last traces of twilight blue are fading. The midnight zone is opening before us, vast and dark and quiet. The water is cold. The pressure is rising, and the world is becoming simpler and slower and more still. Let your breath follow the rhythm of the deep, slow and even, in and out, quiet as the dark water around you. You are sinking gently. There is nothing to be afraid of. The dark is soft here. The deep ocean is very cold. Not cold in the way that a glass of water from the refrigerator is cold. Not cold in the way that a winter morning feels cold when you step outside. The cold of the deep ocean is a more complete and ancient kind of cold. It is a cold that has been there for a very long time. A cold that is stable and steady and utterly consistent, pressing in from every direction, unchanging with the seasons, unchanged for centuries and longer. It is a cold that slows everything down, that quiets everything, that turns the pace of the deep ocean into something slow and deep and patient beyond anything we are accustomed to on the surface of the world. Let us think about why the deep ocean is so cold and how that coldness shapes everything that lives and moves within it. Near the surface, the ocean is warmed by sunlight. In tropical regions, the surface water can reach temperatures of 30 degrees Celsius, or even a little higher on warm, calm days. Even in colder parts of the world, the surface layer of the ocean is relatively warm compared to what lies below. This warm surface water floats. It sits on top of the colder, denser water beneath it, like a thin layer of warm air near a ceiling. But as you descend through the water column, the temperature does not drop gradually and evenly. Instead, there is a zone where the temperature changes very rapidly with depth. This zone is called the thermocline. If you were diving and you passed through the thermocline, you would feel it immediately. One moment, the water is pleasantly cool, The next moment, within just a few meters of descent, it is suddenly much colder. A sharp, startling change. The thermocline acts as a kind of invisible wall between the warm, sunlit world of the surface ocean and the cold, dark world below. Below the thermocline, the temperature continues to drop as you descend, though more gradually. By the time you have reached a depth of 1,000 meters, the water temperature is typically somewhere between 2 and 4 degrees Celsius, just a few degrees above the freezing point of fresh water. Though the salt content of seawater means it does not freeze at this temperature. From 1,000 meters all the way down to the seafloor, the temperature changes very little. In the abyssal depths, the average temperature of the water is around 2 degrees Celsius. Cold, still, and steady. Where does all this cold come from? The answer lies at the poles of our planet, near the North Pole and around Antarctica. The surface of the ocean is very cold indeed. In winter, the sea surface temperature in these regions drops far below 0 Celsius, and sea ice forms when seawater freezes into sea ice. An important thing happens. The salt in the water does not easily fit into the crystal structure of ice. So, as the ice forms, much of the salt is pushed out, left behind in the liquid water beneath. This makes the remaining water saltier, and saltier water is denser. Denser water is heavier, and heavy water sinks. In the polar regions, this dense, cold, salty water sinks from the surface and begins a long, slow journey along the ocean floor. It spreads outward from the poles, flowing along the bottom of the Atlantic Ocean, the Pacific Ocean, the Indian Ocean, filling the deepest basins of the world with cold, dense water. This process is called thermohaline circulation, from the Greek words for heat and salt. It is one of the great engines of our planet's climate system. Scientists sometimes call this the global ocean conveyor belt, and it is an apt name. It is a conveyor carrying water, heat, salt, oxygen, and nutrients from one part of the world to another. But it is a conveyor that moves at an almost unimaginably slow pace. Water that sinks near the North Atlantic or near Antarctica may travel along the deep seafloor for hundreds and hundreds of years before eventually upwelling to the surface somewhere else in the world. Some estimates suggest that a single parcel of deep ocean water takes around 1,000 years to complete the full journey around the global conveyor belt. 1,000 years, that water currently sitting in the deep Pacific Ocean may have last seen the surface of the world at a time when cathedrals were being built in Europe, when empires in Asia were at the height of their power, when the ancestors of people alive today were living lives utterly unrecognizable to us. And through all that time, that water has been drifting slowly and quietly through the cold and dark of the deep ocean, carrying its cold temperature, its oxygen, its dissolved minerals, patiently completing its slow circuit of the world. There is something extraordinary about that thought, about the slow patience of water. In the deep ocean, cold is not just a condition. It is a rhythm, a pace. Everything in the cold deep slows down. Chemical reactions proceed more slowly in cold water. The metabolisms of the creatures that live there run at a lower rate than those of their warm water relatives. Their hearts beat more slowly. Their movements are more deliberate and less frequent. Their lives, in many cases, stretch out for much longer than those of similar creatures nearer the surface. Some deep-sea fish are believed to grow just a few millimeters per year, compared to the centimeters per month of fish in warm surface waters. Some deep-sea corals, growing in the cold and dark at several hundred meters depth, may add only a centimeter of new growth every 10 years. There are deep-sea clams that have been aged at over 100 years old, a species of deep-sea shark called the Greenland shark, which lives in cold, deep water in the North Atlantic, has been studied using radiocarbon dating of its eye tissue. The results suggested that some Greenland sharks may live for 400 years or more, perhaps even 500 years. 400 years, 500 years. An animal that was a young shark when William Shakespeare was alive, a creature that has been moving slowly through the cold, dark water, while the entire modern world came into being above it. The cold slows time. That is the best way to think about it. In the deep ocean, time moves differently, not in any mystical sense, but in the very real biological sense that cold water slows metabolism, slows growth, slows reproduction, and extends the span of a life. The deep ocean is a place where ancient things are still alive, where a colony of cold water coral on a seamount might have been growing for thousands of years, adding its slow millimeter by millimeter of new skeleton to structures that were already old when the first explorers arrived in the Americas. The thermocline, that sharp boundary between warm and cold water, does more than just divide two temperature zones. It also acts as a barrier to mixing. The warm, light surface water and the cold, dense, deep water do not easily combine. The thermocline keeps them mostly separate. Two distinct worlds layered one upon the other, like oil and water in a bottle. This separation has important consequences for life in the ocean. Nutrients, the chemical building blocks that phytoplankton need to grow, and that ultimately feed the entire ocean food chain, tend to accumulate in the cold, deep water. They sink there as particles from the surface, and they stay there, locked below the thermocline, unable to mix back up easily. This is why the open ocean surface in many parts of the world, far from the coasts, is often described as a biological desert, beautifully clear blue water, but relatively poor in life, because the nutrients it needs are all locked below the thermocline in the cold deep. In places where cold deep water does come to the surface, usually where winds or the shape of the coastline force it upward in a process called upwelling, the result is an explosion of life. The cold, nutrient-rich water pours into the sunlit zone, and the phytoplankton respond immediately, blooming in great green and gold clouds that support fish and seabirds and whales, and everything that feeds on them. The cold of the deep, when it meets the light of the surface, is enormously fertile. But in most of the deep ocean, that cold remains quietly below, stable, still, moving only at the pace of the great slow conveyor, carrying its cargo of cold and salt and dissolved oxygen through the dark on a journey of centuries. The abyssal water that fills the deepest basins of the ocean has been there for a very long time. It is ancient water, water that has not seen the surface of the world in centuries. Water that is older than any living person, older than any nation on earth, older than most of the languages we speak. It carries with it a kind of patience that is almost beyond imagination. And down here, in the cold and the quiet, that patience feels entirely natural. There is no urgency here. The cold takes the urgency away and replaces it with something steady and deep and restful. Feel the coolness of the water. Feel it slow everything gently down. Your thoughts, your breath, the pace of everything. You are in the deep cold now, and it is very still and very quiet, and there is all the time in the world. There is something very ancient about pressure. We feel it in small ways every day. The gentle weight of a blanket, the reassuring press of a firm mattress beneath our back, the way a warm room holds us when it is cold outside. Pressure in the right measure is not a threatening thing. It is a containing thing, a settling thing. It tells the body that something solid and present is surrounding it, and in that surrounding there is a kind of comfort. The deep ocean understands pressure in a way that nothing on land ever could. Let us begin at the surface of the sea, where you are floating gently in still water. The air above you weighs down on every square centimeter of your body with the pressure of one atmosphere. This is the pressure we are all born into, the pressure we carry without noticing, the pressure of the entire column of air above us stretching up through the atmosphere. One atmosphere, normal, unremarkable, the pressure of being alive on the surface of the world. Now you begin to sink. For every 10 meters you descend into the ocean, the pressure increases by 1 additional atmosphere at 10 meters below the surface. The pressure on your body is 2 atmospheres. twice what it was at the surface. At 20 meters, it is 3 atmospheres. At 100 meters, it is 11 atmospheres, 11 times the pressure you feel standing on land. You would begin to feel this long before you reached 100 meters. Even at just a few meters depth, the pressure makes itself known in the ears and sinuses. A fullness, a tightening, a gentle insistence that you are somewhere different now. At 1,000 meters, the pressure is around 100 atmospheres, 100 times the pressure at the surface. At this depth, the pressure is roughly equivalent to the weight of a small car, resting on every single square centimeter of your body, every centimeter, all at once, from all directions simultaneously. At 4,000 meters, the average depth of the ocean floor, the pressure is around 400 times what it is at the surface and at the very bottom of the Mariana Trench. At nearly 11,000 meters depth, the pressure reaches over 1,000 times the pressure at sea level. Scientists have measured it at around 1,086 bars, a number so large it is difficult to place in any familiar context. One way to imagine it is this. At the bottom of the Mariana Trench, the pressure is roughly equivalent to standing under a stack of 100 fully grown elephants. Every square centimeter of your body pressed by that incomprehensible weight, every surface, every cavity, every soft tissue compressed. A human being cannot survive at those depths without extraordinary protection. Our bodies contain air-filled spaces, our lungs, our sinuses, spaces behind the eardrums that would collapse instantly under such pressure. The nitrogen in the air we breathe would dissolve into our blood in dangerous quantities long before we reached such depths. Even experienced scuba divers, breathing pressurized air, can only safely descend to around 40 meters before the dissolved gases in their blood become a serious concern. And yet, the deep ocean is full of living things, animals that exist quite comfortably at these pressures, animals that have lived for millions of generations in an environment that would kill a human being in seconds. How do they do it? The answer is elegant, and it begins with a simple principle. The problem of pressure is largely a problem of air. Air is compressible. Water is not, or at least not in any meaningful way at these depths. When pressure acts on an air-filled cavity, it crushes that cavity inward. The walls collapse. The space is destroyed. This is why a sealed polystyrene cup sent down to abyssal depths comes back compressed to a tiny fraction of its original size. The air inside was crushed by the pressure, and the foam walls followed it inward. But a creature that contains no air has no compressible spaces for pressure to crush. Water-filled tissues compress only negligibly, even under the enormous pressures of the deep ocean. And so deep-sea animals have, over millions of years of evolution, eliminated air from their bodies almost entirely. Shallow water fish use a gas-filled organ called a swim bladder to control their buoyancy, to rise or sink in the water column by adjusting the amount of gas inside this internal balloon. It is a beautiful and efficient system in shallow water. But a gas-filled swim bladder in the deep ocean would be crushed flat, or it would require enormous physiological energy to maintain against the surrounding pressure. Deep-sea fish have solved this problem in different ways. Many of them have replaced the gas-filled swim bladder with a liver rich in oily, low-density fats that provide buoyancy without the need for any compressible gas at all. Others have done away with buoyancy control altogether, allowing themselves to be very slightly denser than the water around them, and simply resting on or near the seafloor. Some deep-sea creatures are almost entirely gelatinous, their bodies made up largely of water, with very little solid structure at all. A body made of water, surrounded by water, has almost no pressure differential to contend with. The pressure outside and inside the body are essentially the same. There is nothing to crush, because there is nothing that is different from the water pressing in from all sides. The bones of deep-sea animals reflect this need for flexibility under pressure, where shallow water animals and land animals tend to have dense, rigid, calcified skeletons built to support weight and resist force. Deep-sea creatures often have much lighter, more flexible skeletal structures, soft cartilage rather than hard bone, joints that flex rather than lock, bodies that can give a little under pressure rather than resisting it rigidly and risking fracture. Even the molecules inside deep-sea animals have adapted to the pressure. The cell membranes of all living things are made of fatty molecules called phospholipids, arranged in a flexible double layer that allows the cell to function. Under high pressure, cell membranes tend to stiffen and become less flexible, which can disrupt the chemical processes that keep a cell alive. Deep-sea animals have evolved cell membranes with different fatty acid compositions, ones that remain flexible and functional even under extreme pressure. It is adaptation at the most intimate molecular level, invisible to the eye, but essential to life in the deep. There is a molecule found in many deep-sea animals called trimethylamine oxide, sometimes shortened simply to a long chemical name that researchers have studied with great interest. This molecule appears to act as a stabilizing agent inside the cells of deep-sea creatures, counteracting the distorting effects of high pressure on the proteins and enzymes that carry out the essential chemistry of life. The deeper the animal lives, the higher the concentration of this molecule tends to be in its tissues. It is as though the animal is carrying a chemical cushion inside every cell, a soft internal padding against the weight of all that water above. And what of the pressure itself, as a sensation, as an experience? We cannot know, of course, what a deep-sea creature experiences. We cannot step inside the awareness of a snailfish drifting along the floor of the Mariana Trench and ask it how the pressure feels. But we can say that for an animal that has evolved in that environment, born into it, grown in it, whose every cell and tissue and molecule is tuned to function within it, the pressure almost certainly does not feel like pressure at all. It simply feels like being, like existing, like the normal condition of the world, just as you, lying still right now, do not feel the weight of the atmosphere pressing down on you from above. You do not feel the one atmosphere of air pressure that surrounds you on all sides. It is simply the condition of being here, of being alive in this place, and it is so familiar that it has no sensation at all. The weight of the sea is like that for the creatures that live within it. It is not a burden. It is simply home. And thinking of it that way, the immense pressure of the deep ocean becomes something different. It becomes not a hostile force, but a defining one. A condition that has shaped extraordinary creatures and extraordinary adaptations over millions of years. A weight that has pressed life into forms of elegance and simplicity that could not have emerged any other way. The weight of the sea is immense, and it presses gently on everything within it, and the things within it are perfectly at ease. Let that weight settle over you now gently, like a warm blanket in a dark and quiet room. Let it press you softly into the stillness beneath you. Let it slow your breathing just a little more. Let it hold you in the deep and comfortable dark. You are held. You are still. And the weight of everything above you is nothing but comfort. If you could drain all the water from the ocean and stand at the edge of what remained, you would see the most dramatic landscape on our planet. Not the mountains of Europe or the canyons of North America or the great plains of Asia. Not any landscape that any human being has ever walked through or painted or written poetry about. The landscape beneath the sea is grander than all of these. Taller mountains, wider plains, deeper valleys, longer ridges, a world of landforms so vast and so varied that even today, with all of our technology, we have only mapped a fraction of it in any meaningful detail. More of the surface of Mars has been mapped with high resolution than the floor of our own ocean. Let us travel across it gently tonight. Let us drift over this hidden world as though we are a slow cloud moving above a silent continent. We begin at the edge of the continents, where the land you know slides gradually beneath the sea. Here, the ocean floor is relatively shallow. A broad, gently sloping shelf called the continental shelf that extends outward from the coastline for distances of anywhere from a few kilometers to several hundred kilometers. The continental shelf is the familiar part of the ocean floor, the part where most commercial fishing takes place, where the light still reaches the bottom in many places, where coral reefs grow and seagrass meadows sway in gentle currents. The continental shelf is the ocean's front porch. But at some point, sometimes quite abruptly, the shelf ends. The seafloor drops away into a much steeper slope called the continental slope. Here, the angle of the descent increases sharply, and the depth increases rapidly. The continental slope carries the seafloor down from the shallow shelf, perhaps a few hundred meters deep, down to the deep ocean basin, several thousand meters below. Along the continental slope, there are often enormous submarine canyons, deep valleys cut into the rock and sediment of the slope by ancient rivers and turbidity currents. Great underwater avalanches of sediment that have carved channels as wide and as deep as the grandest canyons on land. The Hudson Canyon, which begins off the coast of New York, is one such feature, cutting a path across the continental shelf and slope that rivals the Grand Canyon in scale. Beyond the continental slope, the seafloor levels out again into the abyssal plain. The abyssal plains are among the flattest places on Earth. Not flat in the way a city street is flat, with small undulations and imperfections everywhere, flat in an almost absolute way. The abyssal plains are vast, featureless stretches of ocean floor covered in a thick, soft blanket of fine sediment that has drifted down from above over millions of years, layer upon layer, smoothing out every irregularity, filling every hollow, burying every bump and ridge beneath a deep, quiet softness. This sediment falls so slowly that it is almost impossible to imagine. In the abyssal plains far from the continents, sediment accumulates at a rate of less than 1 centimeter every 1,000 years, 1 centimeter per millennium. A grain of sediment that falls from the surface today will come to rest on the abyssal plain below, and then wait undisturbed while thousands of years of further sediment settle on top of it. The sediment layers of the abyssal plains are an extraordinary archive of Earth's history, a record of every change in climate and ocean chemistry and biological activity going back hundreds of millions of years, preserved in the quiet dark. The abyssal plains cover roughly 40% of the ocean floor. They are, by area, the single largest habitat on our planet. And yet, we know almost nothing about what lives there. But the abyssal plain is not entirely unbroken. Rising from its surface, here and there, are seamounts. A seamount is an underwater mountain. It rises from the seafloor, but does not reach the surface of the ocean. It is a mountain that no one can climb, a summit that no flag has ever been planted on. There are estimated to be more than 100,000 seamounts in the ocean that rise at least 1,000 meters above the surrounding seafloor, and there may be many more smaller ones we have not yet detected. Seamounts are almost always volcanic in origin. They form where magma from deep within the earth pushes up through the oceanic crust and piles up over thousands and millions of years into a mountain of hardened rock. Some seamounts rise so high that they break the surface and become islands. The Hawaiian Islands are the tops of a chain of seamounts, formed as the Pacific tectonic plate has moved slowly over a volcanic hotspot deep in the mantle, leaving a trail of volcanic mountains behind it, like footprints in soft earth. The oldest islands in the chain have eroded and sunk below the surface over millions of years, becoming seamounts once more. Some seamounts have flat tops. These are called geos. They were once volcanic islands, with their peaks rising above the sea surface, where the waves and weather slowly eroded them flat. Over millions of years, the oceanic crust beneath them cooled, became denser, and slowly sank, taking the flat-topped mountain with it down below the surface, where it now sits in the deep ocean as a flat-topped underwater plateau. A geo is a kind of geological memory, a preserved record of a time when that place was an island, now sunken and silent, and covered in the slow drift of deep ocean sediment rising above all of these features, even above many seamounts, is the greatest mountain range on Earth. It is called the mid-ocean ridge system, and almost nobody knows its name or has any sense of its extraordinary scale. The mid-ocean ridge system stretches for nearly 65,000 kilometers through every ocean basin on the planet. It is a continuous chain of underwater mountains connected from ocean to ocean, winding across the seafloor like the seam on a tennis ball. If you were to stand at the crest of the mid-ocean ridge in the Atlantic Ocean, you would be at the top of a mountain range that is 4,000 meters tall from base to peak in many places, and hundreds of kilometers wide, and it runs the entire length of the Atlantic, from the far north to the far south, a distance of more than 15,000 kilometers. The mid-ocean ridge is not just a mountain range. It is a wound in the Earth's crust. It is the place where two tectonic plates are slowly pulling apart, where the seafloor is cracking open, and where molten rock from the mantle below is constantly rising to fill the gap, cooling in the cold, deep water and solidifying into new oceanic crust. The mid-ocean ridge is where new seafloor is being born. At its crest, the rock is young and hot and rough. As you move away from the ridge in either direction, the rock grows older and cooler and denser, and the seafloor gradually sinks lower, settling down into the abyssal plain far from the ridge crest. The entire floor of the ocean, from ridge to plain, is a record of this slow process of creation and cooling, written in rock over tens of millions of years. And then there are the trenches. The ocean trenches are the deepest places on Earth, long, narrow valleys, where one tectonic plate is being pushed beneath another in a process called subduction. As the old, dense, cool oceanic crust is bent downward into the mantle, it forms a steep depression in the seafloor, a trench. Some of these trenches are staggeringly deep. The Mariana Trench in the western Pacific Ocean is the deepest. It runs for more than 2,500 kilometers in a gentle crescent shape east of the Philippines, and its deepest point, Challenger Deep, plunges to nearly 11,000 meters below the surface. The Mariana Trench is deeper than Mount Everest is tall. If you were to lower the summit of the highest mountain on land into Challenger Deep, the peak would still be more than 2 kilometers beneath the waves. The trenches are not just the deepest places on Earth. They are also among the most geologically active. The process of subduction, where one plate slides beneath another, generates enormous earthquakes and feeds chains of volcanoes on the overriding plate. The Pacific Ring of Fire, that great circle of volcanic and seismic activity that rings the Pacific Ocean, exists in large part because of the trenches and the subduction zones associated with them. And yet, even in the trenches, life persists. Small, soft, strange creatures have been found at the very bottom of the Mariana Trench. Amphipods, small crustaceans like tiny shrimps, living in the Hadal Zone, the deepest realm of the ocean, named for Hades, the ancient Greek god of the underworld. Sea cucumbers, polychaete worms, microorganisms living in the sediment, carrying out their quiet chemistry at pressures that would flat a submarine. Life has found a way into every corner of this hidden landscape. When you think of the seafloor as a landscape, as a world of mountains and plains and valleys and ridges, it changes something about how you imagine the deep ocean. It is not a featureless void. It is not an empty black space. It is a terrain as varied and as structured as any continent. A landscape of extraordinary scale, extraordinary age, and extraordinary quiet, hidden beneath kilometers of cold, dark water. Picture it now, the vast, flat softness of the abyssal plains, stretching for thousands of kilometers in every direction, covered in their slow blanket of settling sediment. Here and there, the dark silhouettes of seamounts rising from the plain, their flanks draped in slow-moving deep-sea currents, and running through the middle of it all, the great winding scar of the mid-ocean ridge, its crest glowing faintly here and there new rock rising from the mantle, and at the edges, the deep, narrow darkness of the trenches. Silent, still, deeper than anything on land. You are floating above all of this now, very high above it, very still. Below you, the landscape of the hidden world stretches away in all directions, slow and dark and old beyond imagination, and it is very, very beautiful. Rest here for a moment, just floating, just drifting, very slowly, over the mountains and plains of the deep. It is snowing in the deep ocean. Right now, at this very moment, in every ocean on our planet, in the cold, dark water below the sunlit zone, tiny particles of organic matter are drifting downward through the water column. Slowly, silently, steadily, a continuous, gentle, invisible snowfall that has been falling in the deep ocean for hundreds of millions of years. A snowfall that no human eye unaided could see from the surface, and that only became known to science when researchers sent cameras and instruments deep enough to observe it directly. Scientists call it marine snow. The name is perfect. When you shine a light through deep ocean water, these particles appear exactly as their name suggests. A soft, drifting snowfall, flakes of white and pale gray, tumbling slowly through the dark water in the beam of a submersible's lamp. Some particles are tiny, barely visible. Others have aggregated into larger, more complex clumps, perhaps the size of a small coin, intricate and fragile, drifting with an unhurried grace that seems entirely indifferent to the extraordinary journey they are making. What is marine snow made of? It is made of everything that lives and dies, and excretes and sheds near the surface of the ocean. Tiny fragments of dead phytoplankton, the microscopic plant-like organisms that live in the sunlit zone and form the very base of the ocean food chain, pieces of dead zooplankton, the small animals that graze on the phytoplankton, fecal pellets produced by animals throughout the water column, packages of waste material wrapped in a thin membrane and denser than the surrounding water, so they sink with surprising speed, shed pieces of skin and shell mucus threads produced by animals called salps and larvaceans that spin elaborate feeding structures from their own secretions and then abandon them when the structures become clogged, releasing great transparent drifting webs into the water, clumps of bacteria, mineral particles. All of these things sticking together as they drift, gathering more material as they fall, growing slowly larger and more complex as they descend. Marine snow is also often described as sticky. Many of the biological molecules in these particles, the proteins, the polysaccharides, the remnants of cell walls, are naturally adhesive. As particles drift through the water, they collect other particles. Smaller flakes stick to larger ones. Bacteria attach themselves and begin to decompose the organic material. The aggregate grows, and then it encounters a current or the feeding appendage of some small crustacean, and it is broken apart again, its components redistributed into the water to begin their slow descent again in a different form. The journey of a marine snow particle from the sunlit surface to the deep seafloor is a long and complicated one. It is not a simple fall. It is an odyssey of decomposition, aggregation, consumption, and re-release, played out over weeks or months as the particle makes its way downward through the water column, and much of it never arrives. By some estimates, only about 1 or 2% of the organic material produced at the surface of the ocean actually reaches the deep seafloor as marine snow. The other 98 or 99% is consumed, decomposed, or dissolved long before it gets there. Every layer of the ocean through which the snow must pass is populated with animals and bacteria, eagerly consuming whatever drifts by. The twilight zone is particularly voracious. The multitudes of small fish and crustaceans and gelatinous animals that live there are constantly filtering the water, catching particles, consuming marine snow as fast as it descends. But that 1 or 2% that does make it all the way down is enormously important. For the animals of the deep seafloor, the abyssal plain, the benthic zone, marine snow is the primary source of food. not the only source, but the foundation on which almost everything else depends. A slow, steady rain of nutrition falling from a surface world that is thousands of meters away and utterly unreachable. The animals of the deep have built their entire existence around this slow and unpredictable supply of food drifting down through the dark. Sea cucumbers, those slow, sausage-shaped animals that move across the abyssal plain in great numbers in some places, feed by sweeping marine snow and the fine organic-rich sediment. It settles directly into their mouths as they plow across the seafloor. Brittle stars extend their long, flexible arms across the surface of the sediment, catching particles as they drift down. Deep-sea sea urchins graze slowly across the sediment surface, processing enormous quantities of it to extract the tiny fraction of organic nutrition it contains. And sitting still in the water above the seafloor, deep-sea sea fans and sponges and stalked crinoids hold their feeding structures into the current, trapping marine snow as it drifts past. Everything in the deep food web traces back, ultimately to the surface, to the sunlight that powers the phytoplankton, to the photosynthesis that converts that sunlight into organic matter, to the great complex food chain of the surface ocean that consumes and recycles and packages that organic matter into 1,000 different forms. And then to the slow fall of all of it, eventually downward through the dark, in the form of marine snow. The deep ocean is, in this sense, completely dependent on the sunlit world above it, even though it never sees the sun. There is something quietly moving about that relationship. The sunlit world above, busy and bright, going about its endless cycles of growth and grazing and reproduction, largely unaware of its own generosity. And the deep world below, patient and dark, receiving whatever falls to it, building entire communities and ecosystems from the small fraction of surface productivity that filters down through all those kilometers of water. Marine snow has another significance beyond simply feeding the deep. It plays an important role in the global carbon cycle. When phytoplankton grow in the sunlit zone, they take in carbon dioxide from the water around them and use it, together with sunlight, to build their tiny bodies. They convert dissolved inorganic carbon into living organic carbon, into the sugars and proteins and fats that make up their cells. When those phytoplankton die and become part of marine snow, and when that marine snow sinks into the deep ocean, they carry that carbon with them, down and away from the surface. If that carbon reaches the deep seafloor and is buried in the sediment, it is effectively removed from the ocean and the atmosphere for thousands or millions of years. It is stored, sequestered, taken out of circulation. This process, the capture of carbon at the surface by photosynthesis and its export to the deep ocean by marine snow, is called the biological pump, and it is one of the most important mechanisms by which our planet regulates the amount of carbon dioxide in the atmosphere. Scientists estimate that the biological pump transfers somewhere between 5 and 12 billion tons of carbon to the deep ocean every year. The white cliffs of Dover, those beautiful chalk formations on the English coast, are in part the remnants of marine snow that fell to an ancient seafloor hundreds of millions of years ago. The accumulated carbonate shells of microscopic plankton, settling over millions of years into a deep, soft layer that was eventually compressed into rock, uplifted by geological forces and exposed at the edge of the sea. Marine snow, falling silently through the dark, has been writing the geological record of our planet for hundreds of millions of years. A slow, patient correspondence between the living surface and the waiting deep. Imagine it now, not as something cold or alien, but as something gentle, as the ocean feeding itself, the sunlit world above sending nourishment downward, grain by grain, flake by flake, into the quiet dark below, a constant and generous snowfall, feeding the brittle stars on the abyssal plain, feeding the sea cucumbers that move so slowly across the sediment, feeding the bacteria in the deep mud, feeding everything that waits in the dark, and the cold for the slow, gentle delivery of what they need. It is snowing in the deep ocean tonight. It has been snowing there for a very long time, and in the quiet of that slow, continuous fall, there is something deeply peaceful. Let it fall around you now, gently. Each thought settling like a soft particle, drifting slowly downward, coming to rest in the quiet dark below. No urgency, no hurry, just the gentle fall. In the deep ocean, there are stars, not the stars of the sky, distant and cold and impossibly far away. These stars are close. They drift past you in the dark water. They pulse softly. They trail long threads of cold light behind them. They hang suspended in the black like the memory of a candle, glowing with a light that comes entirely from within themselves. Alive, patient, lit from the inside by chemistry that is hundreds of millions of years old. Bioluminescence is the ability of a living creature to produce and emit its own light. It is not a rare trick belonging to a few unusual species. In the deep ocean, it is the rule rather than the exception. Around 76% of all animals living in the open ocean are capable of producing light. 76%. More than 3 out of every 4 ocean animals carry within their bodies the chemistry of living light. In the deep sea, below the reach of sunlight, bioluminescence is not a curiosity. It is the dominant form of illumination. It is the only light there is. The chemistry behind this living light is elegant and ancient. Inside the cells of bioluminescent animals, a molecule called luciferin reacts with an enzyme called luciferase. When these two molecules come together in the presence of oxygen, they undergo a chemical reaction that releases energy in the form of light, not heat, not sound, just light, cold, quiet, soft light. The luciferin molecule is oxidized in the reaction, giving up its stored energy as photons. And the luciferase enzyme makes the reaction happen efficiently and at biological temperatures, temperatures that would never produce light through ordinary chemistry. What is remarkable is that this chemistry has evolved independently many times. Bioluminescence did not arise once in a common ancestor, and then spread to all the creatures that now possess it. It evolved again and again in different lineages, in bacteria, in single-celled plankton, in jellyfish, in worms, in crustaceans, in squid, in fish. Each time it evolved, the chemistry was slightly different. The luciferin molecules in different groups of animals are not always the same molecule. Different lineages, facing the same challenge of living in darkness, arrived at the same solution by different chemical routes. Bioluminescence has evolved independently at least 40 times in the history of life on our planet, perhaps more. This convergence is one of the most striking things in all of biology. Independent, unrelated creatures, separated by hundreds of millions of years of evolutionary history, all arriving at the same fundamental answer to the challenge of the dark, all finding, through their own chemistry and their own pressures of survival, the same solution: make your own light. The colors of bioluminescence in the deep ocean are mostly blue and green. This is not coincidence. Blue light travels furthest through water. An animal that emits blue light in the deep ocean can be seen from a much greater distance than one emitting red or orange. Evolution, that patient and relentless force, has tuned these living lanterns to the wavelengths that carry best through the world they inhabit. The result is a deep ocean flickering not with warm gold and amber, but with cool blue and blue-green, the color of stars seen through deep water, the color of something very old and very calm. Let us visit some of the creatures that carry this living light. The anglerfish is perhaps the most famous of all bioluminescent deep-sea animals, and it has earned that fame. The female anglerfish, which is much larger than the male, carries on her head a long, fleshy appendage called an elysium, a fishing rod grown from her own forehead, with a small glowing bulb at its tip. This bulb glows in the darkness of the deep ocean, a small, cold, steady light hanging in the black water. And small animals, attracted to the light, the way insects are drawn to a lamp on a warm night, drift toward it out of the surrounding darkness, the anglerfish waits. She holds her position and she waits. Her enormous mouth, fringed with long, inward curving teeth, hangs slightly open. The Elysium sways gently in the current, its light pulsing, and when something comes close enough, drawn in by the promise of that small glow, the anglerfish strikes. Her mouth opens so wide, so suddenly, that the rush of water into the expanding cavity pulls the prey in before it can react. The light in the anglerfish's lure is not produced by the fish itself. It comes from billions of bioluminescent bacteria living inside the glowing bulb, fed and housed by the fish in exchange for their light. A partnership between a fish and bacteria, maintained in the cold dark at the bottom of the sea. The siphonophore is a creature of an entirely different kind. Not a single animal, but a colony of individual organisms called zooids, each one specialized for a different function. Some zooids are responsible for propulsion, pulsing like tiny bells to move the colony through the water. Some are responsible for feeding, some for reproduction, and some are responsible for light. Some siphonophores can grow to extraordinary lengths, with some species measuring tens of meters from end to end, making them among the longest animals on Earth. And in the dark of the deep ocean, they trail their long, ghostly bodies through the water, lit with chains of blue light that pulse and shift as the colony moves. The vampire squid is a remarkable creature with a name that sounds alarming, but a nature that is anything but. It is not truly a squid, nor truly an octopus, but occupies its own separate group, a living evolutionary relic that has existed largely unchanged for a very long time. The vampire squid lives in the oxygen minimum zone, that layer of the deep ocean where oxygen levels are so low that most predators cannot survive, giving the vampire squid a refuge from danger. It does not hunt, it drifts slowly, using its web-covered arms to catch marine snow drifting down from above. And when threatened, it does not flee or fight. Instead, it ejects a cloud of bioluminescent mucus into the water behind it, a glowing swirling distraction, while the squid wraps its dark cloak of webbed arms around its own body and becomes invisible in the dark. Lanternfish are small, deep-sea fish that are so numerous they may represent the largest total mass of any group of vertebrates on Earth. By day, they rest in the deep, often between 200 and 1,000 meters. By night, many of them migrate upward toward the surface to feed on the plankton blooming there, then return to the depths as dawn approaches. Along their sides and bellies, they carry rows of small, circular photophores, light-producing organs that glow with a soft blue light. The purpose of these lights, scientists believe, is counter-illumination. By producing light on their undersides that matches the dim downwelling light from above, the lanternfish eliminates its own shadow. An animal looking upward from below would see not the silhouette of a fish against the faint light of the sky, but simply a continuation of the even glow. The fish becomes invisible from below by wearing a coat of light. Some deep-sea shrimps, when disturbed or attacked, spray a cloud of bioluminescent fluid from glands near their mouths. The cloud glows briefly in the dark, attracting the attention of whatever was threatening the shrimp, while the shrimp itself darts away through the dark water, a flash of distraction, a small bright sacrifice of light that buys a few moments of escape. Comb jellies, those delicate, transparent animals that drift through the deep like living glass ornaments, produce waves of bioluminescent light that travel around the rings of their iridescent cilia in pulses of blue and green. They do not flash suddenly in alarm. They simply glow steadily and beautifully as they drift. The light may serve to startle predators. It may serve to attract prey, or it may simply be the byproduct of other chemical processes in their transparent bodies. Light produced not as a tool, but simply as a consequence of being alive. Even the seafloor glows. In some parts of the deep ocean, the sediment itself contains bioluminescent bacteria in such numbers that it produces a faint, diffuse glow. And when a sea cucumber or a brittle star moves across the sediment, disturbing it, the bacteria light up briefly, leaving a softly glowing trail in the disturbed sediment behind the moving animal, a trail of cold light on the floor of the deep ocean, fading slowly as the bacteria settle back into stillness. It is a world lit from within, not brightly, not warmly, but persistently, softly, with a kind of patient, scattered illumination that has no source and no direction, that does not cast shadows or reveal landscapes, but that tells you, if you are small and sensitive to light in the deep, that the world around you is not empty, that it is alive, that other things are here in the dark with you. Let that thought settle gently around you now. The deep ocean is alive with its own light, quiet and cold and scattered and blue. And you are drifting through it very slowly, and the lights around you are soft and close and nothing to be afraid of. Just small living stars drifting in the dark. Below 1,000 meters, the last trace of sunlight is gone. There is no blue. There is no shadow. There is no gradient of brightness to tell you which way is up. There is only the dark, pressing in equally from every direction, and the cold, and the weight of all that water above. This is the midnight zone, the bathypelagic zone, and it is the largest single habitat on our planet. 70% of all the water in the ocean is found here, between 1,000 and 4,000 meters depth. This enormous volume of cold, dark, pressurized water is home to creatures that most human beings will never see, living lives so different from our own that they seem to belong to a different world entirely, and in a very real sense, they do. The midnight zone is not a place scientists can visit easily. The pressures between 100 and 400 atmospheres make human presence almost impossible. Without extraordinary engineering, research submarines can descend to these depths, but slowly and carefully, and at enormous expense. Remotely operated vehicles, robot submarines connected by long cables to ships at the surface, have given us glimpses of this world in recent decades, but our glimpses are brief and fragmented. The midnight zone remains, for the most part, unseen, unexplored, full of things we do not yet know. What we do know is extraordinary. The creatures of the midnight zone have been shaped by three absolute conditions: complete darkness, near freezing cold, and crushing pressure. Everything about their bodies, their behavior, their strategies for finding food and avoiding death reflects these three constants. They have had millions of years to perfect their adaptations, and they have done so with a thoroughness that seems almost beyond imagination. Many midnight zone fish are black, not dark, not navy blue, black, an absolute, light-absorbing black that gives no reflection, no sheen, no surface for another animal's bioluminescent light to bounce off. A fish that is perfectly black in a perfectly dark environment is functionally invisible. Dragonfish, those sleek and predatory inhabitants of the midnight zone, have skin so deeply pigmented that it absorbs more than 99% of any light that strikes it. When a dragonfish hunts in the deep, it approaches in darkness and strikes from darkness, its black body invisible even when it is very close. The dragonfish also carries weapons of its own making. Along its chin hangs a long, flexible barbel, a thread of flesh that ends in a small bioluminescent lure. Like the anglerfish with its headlamp, the dragonfish drifts through the dark, with its chin light swaying gently below it, a small invitation of cold blue radiance in the blackness. And the dragonfish has another remarkable tool. Most deep-sea animals produce only blue-green bioluminescence, and most deep-sea eyes can only detect blue-green light, but the dragonfish produces red bioluminescent light from special organs below its eyes. And the dragonfish's eyes are sensitive to red light. Unlike those of almost every other animal in the midnight zone, this means the dragonfish has a private wavelength, a secret torch that illuminates the darkness for it alone, while the animals around it remain completely unaware that a light is shining. The dragonfish can see without being seen. The pelican eel is another remarkable inhabitant of the midnight zone. It is a fish of extraordinary proportions. Its body is long and thin, a deep, dark eel with a tail that ends in a small, glowing pink tip, but its most striking feature is its mouth. The pelican eel's jaws are enormous relative to the size of its body, hinged so loosely that they can open to an angle of 180 degrees, creating a vast, black, membranous pouch like the bill of a pelican. This allows the pelican eel to swallow prey much larger than itself, engulfing whatever comes close in a single, rapid expansion of those extraordinary jaws. In the midnight zone, food is scarce and opportunities are rare. When an opportunity arrives, you must be able to take it, no matter how large or awkward it might be. The pelican eel has evolved a body that wastes no such opportunity. Food scarcity shapes everything about life in the midnight zone. Because so little marine snow makes it this far down, and because there are no plants and no photosynthesis and no upwelling of nutrients, animals in the midnight zone live on very little. Their metabolisms are slow. Their movements are minimal. Many midnight zone animals spend most of their time perfectly still, hovering in the water column, spending as little energy as possible while they wait. Not anxiously, not impatiently, simply waiting with the profound patience of a creature whose entire biology has been tuned to an existence of long stillness, interrupted by rare moments of action. This patience is reflected in body size and structure. Many midnight zone animals are small and gelatinous, their bodies requiring very little energy to maintain. But not all. The midnight zone is also home to some of the largest invertebrates on Earth. The giant squid lives here, a creature of legend and mythology. It swam through the nightmares of ancient sailors as the kraken, a monster capable of pulling whole ships beneath the waves. The reality is no less astonishing. Giant squid can grow to lengths of up to 14 meters from the tips of their longest tentacles to the back of their mantles. They have the largest eyes of any known animal on Earth, each eye up to 25 centimeters across, nearly the size of a dinner plate. These enormous eyes are thought to have evolved specifically to detect the faint bioluminescent flashes that might betray the presence of a sperm whale hunting in the dark. Because sperm whales do come down here, the sperm whale is the largest toothed predator on Earth, a creature that can grow to more than 18 meters in length and dive to depths of 2,000 meters or more in pursuit of its prey. Sperm whales hold their breath, filling their enormous lungs at the surface, and then descend into the midnight zone in a near vertical dive, hunting by echolocation, sending out clicks of sound that bounce off objects in the surrounding darkness and return as echoes. The whale builds a picture of the dark world around it from sound alone, locating squid and fish in the absolute dark as it descends. The evidence of these encounters between sperm whales and giant squid is written on the skin of the whales. Sperm whales are often found bearing circular scars, the marks of giant squid suckers on their faces and heads. These scars speak of enormous struggles in the deep dark. Two great animals locked together, far below the reach of any light, neither visible to any eye in the world. Some beaked whales dive even deeper. The Cuvier's beaked whale has been recorded diving to nearly 3,000 meters, the deepest recorded dive of any mammal. These relatively small, streamlined whales plunge into the midnight zone and beyond, holding their breath for over 2 hours in some recorded dives, hunting deep-sea squid in the total dark. How do they survive the pressure? How do an air-breathing mammal's lungs and tissues withstand the crushing compression of 3,000 meters of water? Their lungs simply collapse under the pressure, compressed to a tiny fraction of their surface volume. The air driven out and absorbed into the bloodstream. Their rib cages flex and compress rather than breaking. Their muscles carry unusually high concentrations of a molecule called myoglobin, which stores oxygen within the muscle tissue itself, allowing the whale to keep its muscles supplied with oxygen even as its lungs collapse. The whale's heart slows dramatically during the dive, routing blood only to the most essential organs. Everything unnecessary shuts down. The whale becomes, during its deep dive, a kind of controlled living compression, a warm-blooded mammal existing briefly in conditions that should be beyond all possibility, and then it rises, slowly at first, then faster, back up through the layers of increasing light, back to the surface, where it draws a great breath of night air and rests in the dark water, heart returning to its normal rhythm, lungs reinflating, muscles recovering, and eventually it dives again. The midnight zone asks extraordinary things of the animals that live in it. But those animals, shaped by millions of years of evolution in exactly this environment, give back extraordinary things in return. It is the world's largest habitat, and it is alive in the dark at this very moment. While you rest here, eyes closed and breathing slowly, the midnight water is carrying on. The dragonfish is drifting through the black, its red light shining for no other eyes but its own. The giant squid is hanging in the cold dark, 3 tentacles extended, waiting. The sperm whale is somewhere above, descending on its long, breath-held hunt, clicking softly into the dark. All of it happening now. All of it quiet. All of it calm. Far below the reach of light, just as you are now, far below the reach of the day. Resting in the dark, very still. Come down now, all the way down, past the midnight zone, past the scattered cold blue flickers of bioluminescence, past the drifting black silhouettes of deep-sea fish hanging motionless in the water column. Come down through the last few hundred meters, where the water grows even colder and even stiller. And now the seafloor is rising toward you slowly out of the dark below. A soft, pale surface, a landscape of extraordinary stillness, and it is alive. The deep seafloor was once thought to be a desert. For a very long time, scientists believed that the deep ocean bottom, that vast, cold, lightless plain so far from the energy of the sun, must be largely lifeless. The reasoning seemed sound. Without light, no plants could grow. Without plants, the base of the food chain was absent. Without a food chain, how could any complex community of animals exist? The deep seafloor, they assumed, must be a biological wasteland, a vast, featureless expanse of cold mud, empty and silent. They were completely wrong. When scientists finally began to sample the deep seafloor properly, trawling carefully through the sediment, examining the animals living in the mud, they found not a desert, but something closer to the opposite. The diversity of life in the deep seafloor sediment rivals that of the richest shallow water habitats. In some estimates, the variety of species living in the deep seafloor sediment may exceed that of a tropical rainforest or a coral reef when measured by the number of different kinds of creatures found in a given area. Not abundance, not density, but variety. The deep seafloor is, in terms of species richness, one of the most biologically diverse habitats on our planet. Despite its coldness, its darkness, and its distance from the sun in proposed deep-sea mining zones alone, scientists have estimated that somewhere between 6,000 and 8,000 animal species remain unknown and unnamed. Around 90% of the species found in one such zone in the Pacific Ocean have never been formally described, never given a Latin name, never studied in any detail. They exist. They have been seen, at least in passing, but they are still, for science, essentially unknown. The seafloor is full of creatures we have not yet met. What does the deep seafloor look like when you arrive? In most places, it is soft. The abyssal plain is covered in a layer of fine, pale sediment. The accumulated marine snow of millions of years, pressed gently into a surface that is almost impossibly smooth over large areas. This sediment is not inert, it is alive. Billions of bacteria and other microorganisms live within it, processing organic matter, cycling nutrients, carrying out the quiet chemistry that keeps the deep seafloor from becoming simply a layer of dead material. The sediment breathes, in a sense. It processes. It turns. Moving across this pale sediment surface are the sea cucumbers. Sea cucumbers are among the most abundant animals on the abyssal plain, and in some areas they are so numerous that they dominate the visible life of the seafloor. They are soft, elongated animals, related distantly to sea urchins and starfish, and they move slowly across the sediment on rows of tiny tube feet, sweeping the surface material into their mouths as they go. A sea cucumber processing the abyssal sediment is extracting nutrition from material so dilute, so fine, so minimally nourishing, that it must process enormous quantities of mud to sustain itself. But it does this continuously, hour after hour, day after day, year after year, moving at the pace of a creature that has all the time in the world. Some sea cucumbers have taken to the water column above the sediment. Swimming sea cucumbers drift just above the seafloor, propelling themselves by undulating their soft, ribbon-like bodies through the water, feeding on marine snow as it falls toward the bottom. They rise a little, feed, and settle again. A gentle rising and falling motion, repeated over and over in the quiet dark. Brittle stars move across the seafloor in a more animated way. Their long, flexible arms flowing over the surface like the fingers of a slow hand, feeling the sediment, withdrawing particles of organic material. Some areas of the abyssal plain are carpeted so densely with brittle stars that the sediment beneath them is almost invisible. The pale arms overlapping and intertwining across the seafloor in every direction, a mat of slow, dark, reaching arms, all feeding on the same fine drift of marine snow, settling to the bottom from above. Standing in one place, rooted to the seafloor, and holding their feeding structures into the current, are the stalked crinoids. These ancient animals look more like plants than animals, and they were once classified as plants by early naturalists who encountered them. A crinoid has a long, flexible stalk anchored to a rock or a fragment of shell on the seafloor, and at the top of the stalk, a crown of feathery arms extended into the water above as the slight current flows past. The crinoid's arms filter out particles of marine snow drifting by. Crinoids modern crinoids were living in ancient seas hundreds of millions of years ago, before the dinosaurs existed, before the great Permian extinction that nearly ended complex life on Earth. They have outlasted catastrophes and mass extinctions and the slow rearrangement of continents. They stand on the deep seafloor now, as they have always stood, patient and quiet, waiting for the snow. Glass sponges grow on the deep seafloor as well, in some areas forming dense fields of extraordinary fragile beauty. These are not the soft, compressible sponges familiar from shallow water. Glass sponges build their bodies from a framework of silica, the same mineral that makes glass and quartz, woven into intricate lattice structures of remarkable delicacy. Some glass sponges grow to heights of 1 meter or more, and their skeletons, when the living tissue is gone, are sometimes called Venus flower baskets. So elaborate and regular is the pattern of silica fiber woven through them. Scientists studying the optical properties of glass sponge skeletons have found that they transmit light through their silica fibers in ways that rival the best human-made fiber optic cables. A glass sponge on the dark seafloor, quietly filtering the deep current for particles of food, carries within its skeleton a technology that human engineers have spent decades trying to replicate. Deep-sea corals also grow on the seafloor, though they are very different from the warm, colorful, sunlight-dependent corals of the tropical shallows. Cold water corals need no symbiotic algae, no sunlight. They feed by filtering the water with their polyps, catching marine snow and small drifting organisms. They grow very slowly, sometimes adding less than 1 centimeter per year, building up over centuries and millennia into reef structures that can be tens of meters tall and thousands of years old. Some cold water coral reefs in the North Atlantic have been dated to 8,000 years or older. They were growing there before the first human civilizations appeared, before the first cities were built, before the first written records were kept. They have been quietly building themselves in the cold dark throughout the entirety of human history. And beneath all of these animals within the sediment itself, a community of creatures so small they are nearly invisible to the naked eye carries on its own quiet existence. Polychaete worms of hundreds of different species thread their way through the sediment, their soft bodies processing it, turning it, mining it for organic material. Small crustaceans, isopods and copepods graze on bacteria, foraminifera, tiny single-celled organisms build elaborate, intricate shells of calcium carbonate and extend thin threads of living tissue into the sediment to capture bacteria and particles. The deep seafloor is not a desert, it is a garden. A slow, cold, dark garden, tended by creatures that move at the pace of decades, growing at the pace of centuries, living in a community that has been established for millions of years and will persist for millions more. One of the most remarkable things about the deep seafloor is its stability. The conditions here, the temperature, the pressure, the salinity, the chemistry of the water have remained essentially constant for thousands, and in some cases millions of years. There are no seasons on the abyssal plain. There are no storms, no droughts, no temperature fluctuations, no sudden changes in light. The world is the same today as it was 1,000 years ago, and as it will be 1,000 years from now. The creatures that live here have evolved for this stability, and some of them reflect it in their extraordinary longevity. This is the seafloor as a living landscape, not dramatic, not fast, not bright, but alive and ancient and unimaginably varied, and patient in a way that puts all human concerns in a quiet and gentle perspective. You are resting on it now, imagining it. The pale, soft sediment beneath you, the slight, cold current above you, the glass sponges standing in their delicate rows nearby, a crinoid somewhere close, its arms extended, filtering the dark water, and over everything, the slow drift of marine snow coming down from the world above, settling quietly. In 1977, a small group of scientists aboard a research submersible descended to the seafloor near the Galapagos Islands in the Pacific Ocean. They were following a geological hunch, the mid-ocean ridge system, that great underwater mountain range we visited earlier in our journey, is a place of geological activity where the plates of the Earth's crust are slowly pulling apart and new rock is forming. Such places, the scientists reasoned, might have warm water seeping from the seafloor, heated by the volcanic rocks below. They were not wrong, but what they found went so far beyond their expectations that it changed. In a single afternoon, everything scientists thought they knew about where life could exist and what life required at a depth of around 2,500 meters. The submersible's lights illuminated a scene that should have been impossible. In a place of total darkness, crushing pressure, and near freezing water, far beyond any reach of sunlight, there was an oasis, a warm, shimmering column of water rising from a crack in the seafloor. And around that crack, clustered in extraordinary abundance, were living things. Enormous creatures living in a world where, by every understanding of biology at the time, they had no right to be. Giant tube worms rose from the seafloor in dense thickets, their white tubes 2 meters long, topped with bright red plumes that waved slowly in the warm current rising from the vent. White crabs moved among them. Pale fish drifted through the water above. Clams as large as dinner plates lay clustered in the warm sediment. Mussels gathered on the rocks. Shrimps swarmed in the rising water. All of it existing in complete independence from the sun. This discovery was one of the most profound scientific revelations of the 20th century. Before 1977, the scientific understanding of life on Earth rested on one unquestioned foundation. Life depended on the sun. Photosynthesis, the conversion of sunlight into organic energy by plants and algae and phytoplankton, was the base of every known food chain. The sun powered everything. Without the sun, there would be no life. The hydrothermal vent communities proved that assumption wrong. Here was an entire ecosystem, rich and complex and thriving, powered not by sunlight, but by the heat and chemistry of the earth itself. The foundation of the hydrothermal vent food chain is chemosynthesis. In photosynthesis, organisms use sunlight to convert carbon dioxide and water into organic matter. In chemosynthesis, bacteria and archaea use chemical energy instead of light energy. At hydrothermal vents, the key chemical is hydrogen sulfide, a compound released in large quantities by the hot water emerging from the vent. Hydrogen sulfide is poisonous to most animals, but certain bacteria have evolved the ability to use it as an energy source, oxidizing it and capturing the released energy to build organic molecules from carbon dioxide. These chemosynthetic bacteria are the primary producers of the vent ecosystem, the equivalent of the phytoplankton of the sunlit ocean, the base upon which everything else depends. The hot water emerging from hydrothermal vents can be extraordinarily hot. Some vents, called black smokers, expel water at temperatures exceeding 400 degrees Celsius. At the surface, water boils at 100 degrees Celsius. But at the extreme pressures of the deep ocean, the boiling point of water is much higher, and the superheated vent fluid emerges as a shimmering, mineral-rich liquid rather than steam. As it meets the surrounding cold seawater, the dissolved minerals in the vent fluid precipitate out of solution, forming a cloud of dark particles that gives black smokers their dramatic appearance. A towering column of what looks like black smoke rising from the seafloor. The minerals that precipitate build up over time, solidifying around the vent, opening into a chimney of rock. These chimneys can grow to heights of tens of meters, and they can grow quite quickly by geological standards. Some black smoker chimneys are thought to grow by tens of centimeters per year, rising slowly from the seafloor like slow-motion towers of stone, sustained by the constant upwelling of hot, mineral-rich water from below. Not all hydrothermal vents are black smokers. Some emit lower temperature water and build chimneys of lighter colored minerals. These are called white smokers. And there are also more diffuse vents, where warm water seeps more gently through cracks and pores in the seafloor without forming dramatic chimneys, creating warm patches of seafloor that host their own communities of life. The giant tube worm, Rifsha pachyptilla, is perhaps the most iconic inhabitant of the hydrothermal vent community, and it is one of the most remarkable animals on Earth. It has no mouth. It has no gut. It has no digestive system at all. It is a worm that has given up eating entirely, at least in the conventional sense. Instead, inside a specialized internal organ called the trophosome, it houses billions of chemosynthetic bacteria. The worm's bright red plume absorbs both oxygen and hydrogen, sulfide from the surrounding water, and delivers them through its bloodstream to the bacteria within. The bacteria, supplied with the chemicals they need, carry out their chemosynthesis and produce organic compounds, sugars, and other nutrients, which the worm absorbs directly. The worm feeds its bacteria. The bacteria feed the worm. A partnership so intimate and so complete that neither could survive without the other. This partnership is reflected in the giant tube worm's extraordinary growth rate in the warm, nutrient-rich environment near a hydrothermal vent. These worms can grow at up to 85 centimeters per year, making them among the fastest growing marine invertebrates known. A worm that was no larger than a finger a few years ago may now stand nearly 2 meters tall, its red plume swaying in the vent current. Among the other remarkable inhabitants of the vent community is the Pompeii worm, named for the Roman city buried by volcanic ash. And with good reason. The Pompeii worm lives on the walls of hydrothermal vent chimneys. In tubes, it constructs from its own secretions, with its tail end extending into water that may be 80 degrees Celsius or hotter, and its feathery head extending out into the slightly cooler ambient water. It tolerates a temperature gradient across its own body that would be lethal to most animals. The Pompeii worm is considered the most heat-tolerant animal on Earth. It survives in temperatures that no other complex animal is known to withstand, sustained partly by a coat of bacteria that live on its back and may help insulate it or detoxify the chemicals in the hot vent water around it. Since that first discovery in 1977, scientists have found more than 500 active hydrothermal vent fields across every ocean basin in the world, from the Arctic to the Antarctic, from the deep Atlantic to the Pacific. Wherever the mid-ocean ridge system winds across the seafloor, vents are being found. Each one hosts its own community of life, and those communities vary from ocean to ocean and from depth to depth. Atlantic vents host different species to Pacific vents. Shallow vents have different communities to those at abyssal depths. The implications of hydrothermal vents extend far beyond the deep ocean. The discovery that life can exist and thrive and build rich and complex ecosystems entirely without sunlight, powered only by chemical energy from within the earth, has profound implications for our understanding of the possibilities of life in the universe. If life can exist in the total darkness of the deep seafloor, powered by geochemistry rather than sunlight, then sunlight is no longer a prerequisite for life. And if sunlight is not a prerequisite, then the range of places in the universe where life might exist expands enormously. Some scientists believe that the subsurface oceans of Jupiter's moon Europa, or Saturn's moon Enceladus, heated from below by tidal forces, might host hydrothermal vents on their seafloors. And wherever there are hydrothermal vents, chemistry happens. And wherever chemistry happens in the right conditions, the possibility of life exists. More than that, some scientists believe that hydrothermal vents may be where life on Earth first began. The chemistry of the early Earth was hostile to life at the surface, but deep in the ocean, where warm, mineral-rich water emerged from cracks in the young seafloor, the chemical conditions were perhaps just right. Some of the earliest evidence for microbial life on Earth comes from rocks formed in ancient hydrothermal vent environments around 4 billion years ago. The vents may be not only a habitat for extraordinary life, they may be the cradle where all life on this this planet first stirred. Think of that gently now as you rest. The warmth you feel, the quiet around you, the dark and the deep, and the hidden heat below, deep within the earth. The same heat that warmed the first living molecules is still rising through the seafloor, still feeding communities of extraordinary animals in the cold and dark, still doing what it has always done, with the patience of a planet that has been alive for 4 billion years. The vents are glowing softly, somewhere far below, and so is everything else. Not all of the deep ocean's hidden oases are hot. In the last section, we visited the hydrothermal vents, those dramatic windows into the Earth's interior, where superheated water erupts from the seafloor and builds towering chimneys of mineral-stained rock, sustaining rich communities of life in the cold dark. The hydrothermal vent is a vivid, dynamic, almost violent kind of habitat. Hot water, dramatic chimneys, fast growth, high energy. But there is another kind of deep-sea oasis that is quieter, slower, and in many ways even more mysterious. It has no dramatic chimney, no column of black or white water rising from a crack in the earth, no heat, no drama, just a slow, almost imperceptible seeping of chemical-rich fluid from the seafloor, so gentle it might seem like nothing at all, and yet around this gentle seep, life gathers in extraordinary abundance. These are the cold seeps. Cold seeps form wherever hydrocarbon-rich fluids, primarily methane gas, but also other compounds, escape slowly from the sediment and rock of the ocean floor. They are called cold seeps to distinguish them from the superheated water of hydrothermal vents. The fluid emerging from a cold seep is not hot. It is roughly the same temperature as the surrounding deep ocean water, just a degree or two above freezing. There is no warmth here, no dramatic temperature difference, just chemistry, a slow breath of methane rising from the sediment, one small bubble at a time, into the cold, dark water above. Where does the methane come from? Beneath the seafloor, buried in the sediment. Enormous quantities quantities of organic material have been accumulating for millions of years. Ancient marine snow, the remains of countless generations of plankton and other sea life, compressed and buried under layer upon layer of newer sediment. Over time, bacteria in the sediment decompose this ancient organic matter, and one of the byproducts of that slow decomposition is methane. As the methane builds up in quantities too large to remain contained within the sediment, it escapes upward through cracks and fissures in the seafloor, rising slowly toward the ocean above. In some places, the methane does not escape directly as a gas. Instead, at the cold temperatures and high pressures of the deep seafloor, methane and water molecules combine to form a strange, icy substance called methane hydrate or methane clathrate. This material looks like ordinary ice, but it contains methane molecules trapped within the crystal lattice of the water ice. Methane hydrates are found in vast quantities in deep ocean sediments all over the world, and they are one of the largest reservoirs of carbon on our planet. They are stable at the cold temperatures and high pressures of the deep. But if they warm, or if the pressure decreases, they dissociate, releasing their methane as gas. A cold seep site on the seafloor is recognizable even before you see it by what leads up to it. Rising from the bottom in fine streams or occasional larger pulses are small bubbles of methane gas, catching the light of a submersible's lamp and sparkling upward through the dark water like slow, ascending pearls. And on the seafloor below these rising bubbles, patches of white and orange bacterial mats spread across the sediment, thick and soft, like a living carpet. These are the chemosynthetic bacteria, the primary producers of the cold seep ecosystem. They absorb the methane and hydrogen sulfide seeping up through the sediment and use the chemical energy locked within those compounds to build organic matter. They are doing, in the cold dark of the deep seafloor, what plants do in sunlight, converting chemical energy into biological material, feeding everything that comes after them, and much comes after them. cold seep communities that build up around these bacterial mats are among the most biologically rich habitats in the deep ocean. They are sometimes described as oases, and the word is apt. In the relative biological desert of the surrounding deep seafloor, a cold seep is a concentration of life, a gathering place, a landscape of abundance in a world of scarcity. Mussels are often among the first visible animals at a cold seep. Not the familiar shallow water mussels of rocky coastlines, but deep sea mussels of a different kind, belonging to a group called Bathymodiolus. These mussels harbor chemosynthetic bacteria within their own gill tissue. In a partnership very similar to the one we saw with the giant tube worms of the hydrothermal vents, the mussels draw in the methane and hydrogen sulfide from the seeping sediment and deliver them to the bacteria living within. The bacteria carry out their chemistry, and the mussel absorbs the organic compounds they produce. The mussel has, in a sense, swallowed its own food factory. It does not need to filter the surrounding water for food particles, as ordinary mussels do. It carries its food source inside its own body. These cold seep mussels cluster in dense beds around active seep sites. Hundreds and thousands of them grouped together on the seafloor, their shells dark against the pale bacterial mats. Other animals gather around them, squat lobsters, small and many-legged, pick their way among the mussel shells, feeding on the bacterial mats or on detritus. Crabs move deliberately through the colony. Shrimps hover in the water just above. Snails graze slowly across the surface of the mats. And where the mussels grow thickly, tubeworms follow. The same kind of chemosynthetic tube worms we saw at the hydrothermal vents, carrying their bacterial partners within their bodies, grow here too, though often in slightly different species, suited to the cold seep environment rather than the hot vent. Their white tubes rise from the seafloor, their red plumes extended into the water, filtering the chemical-rich fluid seeping upward through the sediment beneath them. One of the most intriguing aspects of cold seep communities is the way they change over time. A cold seep is not a permanent fixture. It forms, it flourishes, and eventually it fades as the supply of methane from below is slowly exhausted, or the seep pathway is sealed by the buildup of mineral deposits, and as it changes, the community living upon it changes with it. In the beginning, when a new seep opens, the first colonizers are the bacteria, spreading their pale mats across the fresh seep site. Then the mussels arrive, then the tube worms. The community grows richer and more complex over years and decades as new species arrive to exploit the resources the seep provides. But as the seep ages and the flow of methane begins to slow, the methane-dependent mussels start to die, their beds thin and empty. The bacterial mats shrink, and then, as the seep becomes less active and the chemical flow decreases further, the tube worms too begin to disappear. But the seep does not become empty, because the long years of chemical activity at the seep site have done something lasting. The slow reaction between the seeping methane and the seawater above has gradually precipitated calcium carbonate, a mineral that builds up over time into a layer of hard rock covering the old seep site. And on this hard rock, in the cold dark, cold water corals begin to settle, not drawn by the chemical seep, which is now nearly gone, but drawn by the hard substrate the seep has left behind. They anchor their small polyps to the carbonate rock and begin to grow, filtering the water from marine snow, building their slow coral structures on the foundation that the seep community spent decades creating before them. In this way, a cold seep site goes through a natural succession, a long, slow transition from one kind of community to another, each phase building the conditions for the next. The bacteria make the mats that support the mussels. The mussels and tube worms build the community that precipitates the rock. The rock supports the corals, and the corals, growing over centuries and millennia, create a reef that will outlast the seep that started the whole process by thousands of years. Cold seeps also play an important role in the global climate system. The chemosynthetic bacteria at seep sites consume a very large proportion of the methane rising from the seafloor before it can escape into the ocean water above. They are, in a sense, a biological filter, intercepting methane before it can become a problem. Methane is a potent greenhouse gas, far more effective at trapping heat in the atmosphere than carbon dioxide over short timescales. The bacteria at cold seep sites consume enormous quantities of methane that would otherwise enter the ocean and potentially escape into the atmosphere. Their quiet chemistry, carried out in the cold dark far below the surface, is one of the processes that helps regulate the chemistry of our planet. Enzymes discovered in the microorganisms at deep-sea vent and seep sites have already found practical uses in human technology. One of the most transformative tools in modern biology, the polymerase chain reaction, which allows scientists to make millions of copies of a single strand of DNA, and which is now used in medicine, forensics, and research worldwide, relies on an enzyme originally discovered in a heat-tolerant microorganism from a hydrothermal vent environment. The deep ocean, even in its most distant and extreme corners, has already changed the human world in ways that most people are completely unaware of. Think of it gently. The slow seep of methane through the cold sediment, the pale mats of bacteria spreading across the seafloor, the mussels gathering, the tube worms rising, each one doing what it has always done in the dark and cold far below. The chemistry of the deep seafloor is patient. It works on timescales of decades and centuries. It builds things that last. And right now, in the quiet of the deep ocean, it is carrying on. In every ocean basin, on every continental margin, wherever the chemistry of buried organic matter finds its way slowly upward through the sediment, the seeps are breathing slowly in the dark, and so are you, slowly, quietly, at rest. The deep ocean is full of soft things, not hard things, not dense, armored, rigid things. The deep ocean, especially in the open water column above the seafloor, is dominated by animals with no bones, no shells, no hard skeleton of any kind, animals made mostly of water, held in shapes by the gentlest of biological structures, drifting through the dark with a slow and effortless grace that no land animal could replicate. They are the soft-bodied drifters of the deep, and they are far more numerous, far more diverse, and far more important to the deep oceans functioning than most people realize. In the open water of the deep ocean, being soft is an advantage. On land, or in the shallow sea where predators are fast and alert and abundant, a soft body is a vulnerability, something without armor or a shell, or the ability to run is easy prey. But in the cold, dark, food-scarce deep ocean, the calculus of survival is different. Building and maintaining a hard body requires energy, calcium carbonate for a shell, or phosphate minerals for a bone, must be extracted from the surrounding water and assembled into rigid structures that must be maintained and repaired over a lifetime. In the deep ocean, where food is scarce and energy is precious, that metabolic cost is often too high to justify. A soft, gelatinous body requires far less energy to build and to maintain, and in the near absence of current and turbulence, it can hold its shape without effort. The most familiar of the soft-bodied drifters are the jellyfish. Jellyfish are among the most ancient of all animals. They have been drifting through the ocean for more than 500 million years, long before there were fish, long before there were insects, long before there were plants on land. Their basic body plan, a gelatinous bell with trailing tentacles, has been refined by evolution over those 500 million years into extraordinary diversity. There are hundreds of species of jellyfish in the ocean, from tiny creatures barely a centimeter across to the lion's mane jellyfish, whose bell can reach over 2 meters in diameter, and whose trailing tentacles can extend for 30 meters or more. In the deep ocean, jellyfish take on forms that seem almost too strange to be real. Some deep-sea jellyfish are completely transparent. Their bell and trailing arms perfectly see-through, visible only as a slight distortion in the water when a light catches them at the right angle. Others are a deep, rich red, invisible against the dark water. Their redness the same camouflage trick we saw with the shrimps and crabs of the deep. Some deep-sea jellyfish pulse with bioluminescent rings of blue and green light that trace the edge of their bell as they contract and expand. The comb jellies are often mistaken for jellyfish, but they are something quite different, belonging to their own separate group, with no close relationship to jellyfish at all. Where jellyfish move by pulsing their bells, comb jellies move by beating rows of tiny, hair-like cilia arranged in 8 long combs that run the length of their bodies. As these cilia beat in coordinated waves, they refract light into iridescent rainbows that travel up and down the comb rows in shifting colors. Even in the complete absence of bioluminescence, it is one of the most beautiful sights in the ocean. This slow, living shimmer of rainbow light moving across a transparent body in the cold, dark water. Comb jellies are voracious feeders. Despite their delicate appearance, they engulf prey with their mouths, which can open extraordinarily wide relative to their body size. Some species of comb jelly are thought to consume the equivalent of their own body weight in prey each day. In the deep ocean, where comb jellies can be very abundant, this feeding can have a significant effect on the populations of other small animals and plankton in the water column. The siphonophores are perhaps the most extraordinary of all the soft-bodied drifters. We touched on them briefly when we discussed bioluminescence, but they deserve more attention here. A siphonophore is not a single animal. It is a colony of individual organisms called zooids, each genetically identical to all the others in the colony, but each specialized for a different function. Some zooids are swimming bells, pulsing rhythmically to propel the whole colony through the water. Some are feeding polyps, equipped with stinging tentacles to catch prey. Some are reproductive bodies. Some produce the bioluminescent light, and these zooids are not separate animals living together. They are so intimately connected that they cannot live apart. The swimming bells cannot feed themselves. The feeding polyps cannot move. Each zooid is dependent on every other, and the colony as a whole functions as a single integrated organism. A siphonophore is, in this sense, a fascinating philosophical puzzle. Is it one animal or many? The question may not have a clear answer. It is something in between, something that does not fit neatly into our familiar categories of individual and colony. Some siphonophores grow to extraordinary lengths. One species, Praia dubia, may be the longest animal on Earth, with some specimens believed to reach over 40 meters from one end to the other. This extraordinary length is not the result of any single organism growing large. It is the result of a colony of tiny, specialized individuals, each no bigger than a finger, cooperating so intimately that together they become the longest animal in the sea. They drift through the deep ocean, trailing their tentacles in curtains, waiting. A small fish or a shrimp contacts a tentacle. The stinging cells fire instantly, paralyzing the prey. The feeding zooids draw it inward, and the colony continues its slow drift, maintaining its extraordinary length in the dark water, its swimming bells pulsing in quiet rhythm. Now, let us give attention to the giant squid. Architeuthis ducks, the largest invertebrate on Earth by length, and one of the most mysterious animals that has ever been studied. The giant squid is not a drifter in the way of the jellyfish and siphonophores. It is an active, muscular predator. It has 8 arms lined with suckers edged with sharp, saw-like rings of chitin, and 2 longer feeding tentacles that can shoot outward at remarkable speed to seize prey. It navigates through the dark, deep ocean using its enormous eyes, those remarkable dinner plate-sized structures that are the largest of any known animal alive today, evolved specifically to detect the faint flickers of bioluminescence in the surrounding dark. For most of human history, the giant squid was known only from carcasses washed ashore on beaches. Fragments recovered from the stomachs of sperm whales, and occasional specimens hauled up accidentally in fishing nets. The living animal in its deep ocean habitat had never been seen, never been filmed, never been observed. It was the largest invertebrate on Earth, and science had never witnessed it alive in its natural environment. That changed in 2004 when Japanese researchers managed to capture the first photographs ever taken of a living giant squid in the wild. The animal was at a depth of around 900 meters when it was photographed, and the images showed a creature of extraordinary presence, large and muscular and intensely alert, its arms extended as it moved through the dark water. The photographs caused a sensation. Here at last was the actual living animal, not a dead fragment, not a tooth mark in whale skin, but a real, living giant squid going about its life in the deep ocean. The colossal squid, Mesonichotuthis hamiltoni, is the giant squid's even more massive relative, living in the cold waters around Antarctica at depths of 1,000 meters or more. The colossal squid is heavier than the giant squid, though somewhat shorter in total length. Its tentacles are armed not merely with sucker rings, but with swiveling hooks, rotating blades that can grip prey with extraordinary firmness. A colossal squid caught in Antarctic waters in 2007 weighed nearly 500 kilograms and measured around 4.5 meters in mantle length. It was the largest cephalopod ever recorded, and it was a juvenile. Both the giant squid and the colossal squid remain among the least understood of all large animals on Earth. We have never observed their mating behavior. We do not know how long they live. We do not fully understand their role in the deep ocean food web, though their abundance as prey for sperm whales suggests they must be extraordinarily numerous. In the deep ocean, the soft-bodied drifters and the great muscular squid share the same dark water. The siphonophore trails its 40-meter colony in silence. The comb jelly pulses its rainbow cilia through the cold. The transparent jellyfish hangs motionless, its tentacles extended in a long, invisible curtain. And somewhere deeper, where the water is coldest and darkest, the giant squid moves, patient, alert, enormous, and almost entirely unknown. Let all of that softness settle around you now. The gentle drift of the jellies, the slow pulse of the siphonophore, the cold, dark water giving way to soft bodies on all sides. Everything here is gentle. Everything here is slow, and everything here is drifting very quietly through the dark. The deep ocean is the most creative place on earth. That is not a poetic exaggeration. It is a biological fact. When a group of animals faces a set of extreme conditions over millions of generations, evolution works with extraordinary energy, producing solutions of wild and sometimes astonishing ingenuity. The deep ocean, with its darkness and cold and pressure and scarcity of food, has been producing these solutions for a very long time. And nowhere is the creative power of evolution more visible than in the bodies of the fish that live there. Deep-sea fish do not look like the fish that swim in the shallows. They do not look like the fish you might see in an aquarium or pull gently from a rock pool. They have been shaped by forces entirely different from those that shaped their shallow water relatives. And the result is a collection of animals that seem, at first encounter, barely believable, extravagant mouths, telescoping eyes, bodies that glow or that absorb every particle of light, organs and appendages that seem at first to be errors of design, but reveal themselves on closer examination to be elegant solutions to very specific problems. Let us visit some of them. The barrel-eye fish carries its name honestly. Its most striking feature is its eyes, which are not round, as eyes normally are, but cylindrical, projecting upward from the top of its head, like a pair of glowing green barrels. These tubular eyes are extraordinarily sensitive to light and face upward to detect the silhouettes of small animals passing above, backlit against the faintest downwelling glow from the surface. And the barrel-eye fish has another remarkable feature. Its entire head, from the back of its small mouth to the top of its skull, is covered by a transparent, fluid-filled dome of soft tissue, a living helmet of gel, utterly transparent, through which the glowing green beryl eyes can swivel and pivot. When researchers first encountered this fish alive from underwater vehicles, they were baffled by the anatomy. The fish had been known from dead specimens for decades. But when a fish dies and is brought to the surface, the fluid-filled dome collapses and deflates, leaving only the bare, strange eyes without context. Only living observations revealed the full, extraordinary reality. The hatchetfish earns its name from its compressed, angular body, which viewed from the side resembles the blade of a small hatchet. It lives in the twilight zone between 200 and 1,000 meters, and it faces the challenge of predators lurking below, looking upward. Against the faint, downwelling light from the surface, any animal above such a predator is silhouetted, its dark shape visible against the lighter water. The hatchetfish has solved this problem with counter-illumination, carrying rows of small, downward-facing photophores along its belly. These organs produce a soft light that matches precisely the intensity and color of the light filtering down from above, eliminating the fish's shadow, making it invisible from below against the glow. The hatchetfish is wearing a coat of light, and it does so continuously and automatically, adjusting the brightness of its photophores as the light levels above it change throughout the day. And as it moves up and down in the water column, the tripod fish is a creature of the deepest, still water just above the abyssal plain. It is a small, elongated fish with an unusual way of resting. 3 of its fins, the 2 lower pectoral fins and the lower lobe of its tail fin, have extended into long, stiffened rods that the fish uses as stilts. It stands on the seafloor on these 3 fin rods, its body elevated above the sediment, facing into the current, holding itself perfectly still, and with its mouth open and its remaining fins extended to either side like a pair of outstretched arms, it waits, not actively hunting, not pursuing prey, just standing, waiting for whatever the current brings. A small amphipod a piece of marine snow dense enough to matter. Anything, the tripod fish has eliminated the energy cost of swimming entirely by simply standing and waiting for the food to come to it. It is, in this sense, one of the most energy-efficient predators in the ocean. It does not even move toward its food. It lets the water do all the work. The viperfish is a fish of the twilight zone, small in body, but enormous in ambition. Its jaws carry long, transparent, needle-like fangs, so outsized that they cannot fit inside the fish's mouth when it closes. The fangs simply project forward and outward, curving slightly. A cage of transparent needles arranged around a mouth that can open to an extraordinary angle. When a viperfish strikes at prey, the lower jaw drops on a hinged mechanism. The head tilts back, and the entire front of the fish essentially opens like a trap. The needles curve inward as the jaw moves, ensuring that nothing caught between them can escape. The viperfish is small enough to hold in a hand, but its jaws are designed to catch fish nearly as large as itself. The black swallower is another fish that takes the problem of food scarcity to its logical extreme. It is a small deep-sea fish with a distensible stomach so elastic that it can swallow prey more than twice its own length and 10 times its own mass. The stomach simply expands, stretching to accommodate whatever the black swallower has managed to catch, growing until the fish's body is grotesquely distended by the meal inside it. On several occasions, black swallowers have been found dead at the surface, killed not by predation, but by their own ambition. They had swallowed prey too large to be digested quickly enough, and the decomposing meal had produced gases that expanded inside the distended stomach and floated the fish helplessly to the surface and its death. The snailfish deserves special mention, not for drama, but for a kind of quiet extremism. Several species of snailfish live in the hadal zone, the deepest layer of the ocean found in the trenches, at depths below 6,000 meters. The deepest individual fish ever recorded was a snailfish filmed in the Mariana Trench at a depth of more than 8,300 meters in 2023. It is a pale, soft, small fish with a tadpole-like body, enormous eyes for its size, and a gelatinous consistency that gives it the flexibility to cope with the extreme pressure around it. It lives at the absolute limit of vertebrate life on Earth, in conditions of darkness and pressure and cold that no other fish has been observed surviving. The anglerfish, already briefly encountered in our section on bioluminescence, deserves a further moment of consideration here for what is surely the most extraordinary reproductive strategy in the animal kingdom. The male anglerfish is a tiny creature, barely the size of a finger, and it has one purpose in life. It hatches. It grows just enough to develop a functioning sense of smell, and it searches the dark water for a female. The female is very much larger, perhaps 100 times the mass of the male. When the tiny male finds her, guided by chemical signals in the water, he bites into her side, and then he stays. His mouth fuses with her skin. Over time, his body merges with hers, their circulatory systems connecting, his organs atrophying as he is absorbed. Eventually, only his testes remain functional, permanently attached to the female's body, providing her with sperm whenever she needs it, two animals becoming one. The male sacrifices everything: his eyes, his jaw, his independence, his individual existence, to become part of his mate. In the deep ocean, where finding another individual of your species in the vast dark is extraordinarily difficult and rare, this strategy, however strange it seems, makes perfect biological sense. The bodies of deep-sea fish are a catalog of extraordinary solutions to extraordinary problems. Every strange jaw, every telescoping eye, every glowing belly, every transparent skull is the answer to a question posed by millions of years of darkness and cold and pressure and scarcity. And each answer, however odd it looks when brought into the light of the surface world, is precisely right for the world it was made for. Let the strangeness of these creatures settle gently into your thoughts. Not alarming, just remarkable, quietly, wonderfully remarkable. Bodies shaped by darkness into things the light could never have imagined. And all of them, right now, somewhere in the deep, going about their slow and quiet lives. Beneath everything we have seen in the deep ocean, beneath the giant squid and the glass sponges and the tube worms and the cold seep mussels and the slow drifting marine snow, there is another world, a world so small it is entirely invisible to the naked eye, a world so ancient and so vast that it dwarfs, in terms of total mass and total biological activity, everything else we have discussed, a world that is, in the most literal and fundamental sense, the foundation on which all deep ocean life is built. It is the world of the microbes. Marine microbes, a category that includes bacteria, archaea, fungi, and tiny single-celled organisms, account for more than 98% of all the living matter in the ocean, not 98% of the species, not 98% of the individuals, 98% of the total biological mass. Everything else, all the fish and the squid and the whales and the jellyfish and the sea cucumbers and the corals and the sponges and all the other visible life of the ocean combined, makes up less than 2% of the ocean's total biomass. The microbes are the ocean. Everything else is detail. This is a perspective that takes time to settle in. We are accustomed to thinking of the visible, macroscopic world as the real world, and the invisible microbial world as something secondary, a background hum of biological activity that supports, but does not define the life we can see. In the deep ocean, that perspective is simply wrong. The microbes are primary. They are the majority. They are the foundation, the engine, and in many cases the endpoint of almost every biological process that takes place in the deep. A single milliliter of deep ocean water contains between 1,000 and 10,000 bacterial cells. 1 milliliter, a volume smaller than a single drop of water, and the ocean contains approximately 1.3 billion cubic kilometers of water. The total number of microbial cells in the ocean is a number so large it has no familiar analog. Scientists estimate it at somewhere around 10 to the power of 29. That is a 1 followed by 29 zeros. More microbial cells in the ocean than there are stars in all the observable universe. In the deep ocean water column, bacteria and archaea drift in the cold dark, absorbing dissolved organic compounds from the surrounding water. Even deep in the midnight zone and abyssal zone, far below any sunlight, far below any obvious source of fresh organic material, there is a background level of dissolved organic carbon in the water, ancient, dilute, difficult to access. But the deep ocean bacteria are extraordinarily efficient at extracting energy from even the most dilute and recalcitrant organic compounds. They have evolved enzymes capable of breaking down molecular structures that would resist decomposition for centuries in the surface ocean. In doing so, they are performing one of the most important functions in the ocean's chemistry. When organic matter falls through the water column as marine snow, bacteria attach to each particle and begin to consume and decompose it. They break large organic molecules into smaller ones. They release the nutrients locked within the organic matter back into solution. They consume oxygen in the process, producing carbon dioxide. In this way, bacteria are the great recyclers of the ocean, taking the complex organic structures produced by photosynthesis at the surface and dismantling them step by step, releasing the nutrients and the carbon into forms that can be reused. But the deep ocean sediment is where the story becomes most extraordinary. Beneath the seafloor, buried in the soft sediment of the abyssal plain, are bacteria and archaea living in conditions so extreme, so energy limited, so remote from any obvious source of nutrition, that their existence seems almost impossible. These are the deep subsurface microbes, and they live in the sediment layers accumulated over millions of years at depths of tens or hundreds of meters below the seafloor surface, in complete darkness, with almost no oxygen, almost no food, and almost no energy, and yet they live. drilling into deep ocean sediments, have recovered living bacteria from depths of hundreds of meters below the seafloor, from sediment layers that were deposited millions of years ago. In one remarkable study, researchers recovered living microbial cells from sediment cores taken from the South Pacific Ocean, sediment that was 101.5 million years old. The sediment had been accumulating for over 100 million years. And when researchers added nutrients to the sediment in the laboratory, the microbes responded. They began to grow. They began to divide. Cells that had been existing in the deep sediment since the time of the dinosaurs were still alive, still functional, still capable of waking up when conditions improved. How is this possible? The answer lies in a kind of biological patience that makes the patience of the deep ocean's slow current and cold water corals look hasty by comparison. Deep subsurface microbes have metabolisms so slow that they are almost beyond measurement. Some studies have estimated that the bacteria in deep sediments divide, that is, reproduce, once every 10,000 years. Compared with a bacterium in a warm, nutrient-rich laboratory culture, which can divide every 20 minutes, a bacterium in deep sediment is 1,000,000 times slower. Its entire biochemistry is running at the lowest possible rate, consuming the minimum possible energy, maintaining the cell's fundamental functions at a level just barely sufficient to prevent death. These cells are not dormant in the usual sense. They are not in a spore state or a freezing condition or any kind of suspended animation. They are active. They are metabolizing. They are maintaining their membranes, repairing their DNA, keeping their chemistry ticking over. They are just doing all of this at an inconceivably slow pace, stretched across geological time. The food they are consuming is centuries old. Studies of the carbon in deep sediment bacteria have shown that some of these microbes are eating organic matter that was deposited on the seafloor hundreds or thousands of years ago. They are locked in a slow communion with ancient material, extracting the last traces of chemical energy from compounds that have already been processed and reprocessed by generations of bacteria above them in the sediment column. The archaea deserve particular attention here. Archaea are microorganisms that superficially resemble bacteria, but are genetically quite distinct, forming a separate and ancient domain of life. They are found throughout the ocean, but they are especially important in the deep ocean and in deep sediments. Certain archaea, called ammonia-oxidizing archaea, are extraordinarily abundant in the deep ocean water column, and they play a critical role in the ocean's nitrogen cycle, converting ammonia dissolved in the water into nitrite and then nitrate, forms of nitrogen that other organisms can use. Without this activity, the chemistry of the deep ocean would be fundamentally different, and the supply of nitrogen to organisms throughout the water column would be compromised. Other archaea in the deep sediment carry out the process of methanogenesis, producing methane as a byproduct of their metabolism. These are the organisms that create much of the methane that seeps from the cold seep sites we visited earlier, and other archaea, in combination with bacteria, carry out the anaerobic oxidation of methane, consuming that methane before it can escape into the overlying water. An invisible chemical tug-of-war played out in the deep sediment between microbes that produce methane and microbes that consume it, with the balance between them determining how much of this potent greenhouse gas reaches the ocean, and ultimately the atmosphere. The deep ocean microbes are also remarkable sources of discovery for human science and medicine. The enzymes produced by deep-sea bacteria and archaea, tuned to function at high pressure and low temperature, have proven useful in biotechnology applications. The enzyme used in the polymerase chain reaction, that fundamental tool of modern molecular biology and medical diagnostics, was derived from a bacterium living in a high-temperature geothermal environment. Deep, cold-adapted enzymes are being investigated for applications in food processing, pharmaceuticals, and industrial chemistry, where reactions at low temperatures would be advantageous. The deep ocean microbial world is not only the engine of deep ocean biology, it is also an as yet largely unexplored library of biological and chemical innovation. And the most profound thing of all is how little we know. The vast majority of deep ocean microbial species have never been cultured in a laboratory. Many of them cannot be cultured, at least not with current techniques, because they require the specific conditions of the deep: the pressure, the cold, the absence of oxygen, the specific chemical compounds available in their natural environment, none of which can be easily replicated on a laboratory bench. We know they exist because we can read fragments of their DNA in the water and the sediment. But we have almost no idea what most of them look like, how they function, what chemistry they perform, or what role they play in the deep ocean. The deep ocean microbial world is the largest and least known ecosystem on our planet. It has been there since before the first animals evolved. It will be there long after the last large animal is gone. It is running quietly right now, at this very moment, in the cold, dark sediment under all the world's oceans. Patient, ancient, invisible, essential, and utterly at peace in the dark. As you are now, breathing slowly, each breath like a slow microbial cycle, taking in what you need, releasing what you don't, resting in the quiet chemistry of being alive. Everything in the deep ocean is a problem to be solved, not a catastrophic problem, not a crisis, just the steady, patient, long-term problem of existence in a place that offers very little and demands a great deal. The deep ocean asks its inhabitants to survive crushing pressure, to function in near-freezing cold, to navigate in complete darkness, and to sustain themselves on a food supply so sparse and so unpredictable that it would starve almost any creature from the sunlit world above within days. And the animals of the deep have answered every one of these demands with solutions so refined and so precise that they feel, when you examine them, less like compromises and more like masterpieces. We have touched on many of these adaptations already in our journey. Bioluminescent lures, expandable jaws, transparent bodies, bacterial partnerships. But tonight, let us slow down even further and consider the deep philosophy of survival in the deep ocean, the principles that underlie all these specific solutions. The logic of a life lived where light is absent and food is rare. The first principle is economy. In the deep ocean, energy is the scarcest resource of all. Food arrives slowly, intermittently, and in small quantities. An animal that wastes energy unnecessarily, that swims when it could drift, that maintains a large and metabolically expensive body when a small and simple one would do, will eventually run out of the reserves it needs to function. Evolution in the deep ocean is evolution toward thrift, toward doing the most with the least. This economy expresses itself in metabolic rate. Deep-sea animals, almost without exception, have lower metabolic rates than their shallow water relatives of comparable size. Their hearts beat more slowly. Their cells consume oxygen more slowly. Their biochemical reactions proceed at a lower rate. This is partly an inevitable consequence of cold water, which slows chemistry of all kinds, but in many deep-sea species, the low metabolic rate goes beyond what cold alone can explain. It appears to be an active adaptation, a tuning of the body's chemistry toward a lower energy setting, maintained even when the animal is brought into warmer water. The Greenland shark offers one of the most striking examples of where this metabolic economy can lead. Living in the cold, deep water of the North Atlantic and Arctic Ocean, the Greenland shark has one of the lowest metabolic rates of any vertebrate. It grows almost imperceptibly slowly, reaching sexual maturity only at around 150 years of age. And it lives for an extraordinary length of time. Studies using radiocarbon dating have suggested that some Greenland sharks may live for 400 years or more, with one individual estimated to be nearly 500 years old. A single animal alive for half a millennium, moving slowly through the cold, dark water, sustained by a metabolic rate so slow it barely registers. The second principle of deep ocean survival is flexibility in an environment where food arrives unpredictably, sometimes in a small, steady trickle, and sometimes when a whale falls to the seafloor in an enormous, sudden abundance. Deep-sea animals have evolved bodies and behaviors capable of responding to both extremes. Many deep-sea animals can fast for extraordinarily long periods. Their bodies are built for storage, extra lipid reserves, expandable stomachs, the ability to slow their metabolism even further during lean periods, and then to accelerate it and eat voraciously when food is suddenly available. Some deep-sea fish can consume prey several times their own body weight in a single meal, storing the excess in a distensible stomach that may take weeks or even a month to fully digest. The black swallower and the deep-sea gulper eel both have elastic, expandable stomachs capable of this kind of feast and fast cycle. They may go weeks or months between significant meals, slowly digesting a single large catch while waiting motionless in the dark for the next opportunity. Deep-sea isopods, those large, flattened crustaceans that resemble giant woodlice and can grow to remarkable sizes, have been observed in experiments consuming enormous quantities of food when it is provided, and then surviving for months, even years, in laboratory conditions without any further feeding. Their physiology allows them to enter a state of dramatically reduced metabolic activity when food is absent, waiting out the lean times with remarkable patience. This capacity to eat enormously when food is present and to sustain oneself on almost nothing when it is absent is perhaps the most fundamental adaptation to the deep ocean food environment. The third principle is minimalism of structure. Building a body costs energy. Every gram of tissue, every organ, every skeletal element requires energy to produce and energy to maintain. In the deep ocean, where energy is precious, animals have evolved to build only what is absolutely necessary and to reduce or eliminate what is not. Eyes cost energy in the complete darkness of the abyssal zone and the deepest parts of the midnight zone, where no light of any kind reaches. Eyes are useless. Evolution, that relentless economist, has responded by reducing or eliminating eyes in animals that live in regions of permanent, total darkness. Some abyssal fish have tiny vestigial eyes that are essentially functionless, remnants of ancestors that lived in shallower, lighter water. Others have no eyes at all. The tripod fish, standing on its fin stilts on the abyssal plain, relies instead on highly sensitive extensions of its lateral line system, a network of pressure-sensing cells that detects the movement of water caused by approaching animals. It has traded vision for vibration. Color costs energy too. The pigment molecules needed to produce color in skin or scales require metabolic investment to synthesize in the deep ocean, where there is no light to illuminate color, and no eyes sensitive to most wavelengths anyway. Color loses most of its purpose. Many deep-sea animals are simply black, the cheapest possible option, requiring only the most common and easily produced dark pigment. Others are white or pale gray. The color of animals that have lost pigmentation entirely over the generations, their cells no longer devoting any metabolic resource to the production of color, they have no use for. Dense bones and rigid skeletons are expensive. In the deep ocean, buoyancy is a constant challenge, and dense bone makes an animal heavier, requiring more energy to maintain position in the water. Many deep-sea fish have reduced their skeletal density dramatically, replacing heavy mineralized bone with flexible cartilage or lighter, less calcified bone. Their bodies have more water in their tissues, making them closer in density to the surrounding seawater and reducing the energy needed to remain neutrally buoyant. The result of this minimalist approach to body design is that many deep-sea fish, when brought to the surface, seem extraordinarily fragile and insubstantial. They are soft. Their tissues are watery easily damaged. Their bones flex rather than resist. These are not deficiencies. They are solutions refined over millions of generations, perfectly suited to the conditions of the deep. In the context of the deep ocean, these bodies are not fragile at all. They are exactly strong enough, exactly dense enough, exactly structured enough. Not a gram more than necessary. The fourth and final principle is patience. Patience is not a strategy in the conscious sense. The animals of the deep ocean do not choose to be patient. They simply are. Their biology runs slowly. Their reproductive cycles are long. Their lives stretch across decades and centuries. They do not rush. There is no rushing here. The cold and the dark and the scarcity of food have shaped a world in which slow is not a disadvantage, but an adaptation. Slow metabolism, slow growth, slow reproduction, long life, a deep-sea orange roughy fish caught in commercial fishing nets in the deep waters of the Southern Ocean may be 150 years old when it is caught. It grew so slowly, reproduced so infrequently, and lived so long that a single commercial fishing operation can eliminate in a season what took centuries to accumulate. The deep ocean does not replace its life quickly. It cannot. Its entire biology is tuned to a pace that the surface world finds almost incomprehensible. This is the patience of the deep, not a virtue chosen, but a condition lived, a condition that shapes every cell and every behavior and every breath of every animal down there. And it is, in its own quiet way, a kind of wisdom. The deep ocean's lesson to everything that lives within it is simple. Slow down. Use only what you need. Wait for what you require. Build nothing you do not need. And trust that time, vast and unhurried, will provide. Carry that lesson with you now into the rest of this night. Slow down. Use only what you need and rest. The deep ocean is not silent. This might seem surprising. We have spent so much of our journey together describing the darkness and the stillness and the cold quiet of the deep. That silence seems to belong here naturally And there is a quality to the deep ocean that could fairly be called quiet. No wind, no rustling of leaves, no rainfall, no traffic, no voices. In that sense, the deep ocean is a place of extraordinary calm, but water carries sound in ways that air does not. Sound travels through water roughly 5 times faster than through air, and water carries sound much further than air without the scattering and absorption that quickly diminishes sounds in the open atmosphere. The deep ocean is threaded through with sound. Low sounds, long sounds, sounds that travel for distances that have no equivalent on land. Sounds produced by volcanoes on the mid-ocean ridge, by earthquakes rumbling through the seafloor, by the movement of ice far above in the polar regions, and most beautifully by whales. Deep in the ocean, at a depth of around 700 to 1200 meters, depending on the temperature and salinity of the water in that region, there is a layer where the speed of sound reaches its minimum. Above this layer, sound travels faster as the water warms toward the surface. Below it, sound travels faster as the pressure increases with depth. At the layer itself, the speed of sound is at its lowest point, and physics dictates that sound waves, like light, bend toward regions of lower speed. Sound produced in or near this minimum speed layer bends both upward and downward toward the layer, and in doing so, it becomes trapped, channeled. Scientists call this the SOFAR channel. It stands for sound fixing and ranging channel, but the name is less important than the phenomenon itself. The SOFAR channel is a natural acoustic waveguide running through the ocean, an invisible highway of channeled sound that encircles the entire planet at mid-depths, and through which sound can travel for extraordinary distances without significant loss of energy. Sound entering the SOFAR channel can travel across entire ocean basins. Low-frequency sounds produced in the Atlantic Ocean have been detected by instruments in the Pacific. Whale calls entering the channel at the right frequency can, in theory, be heard by other whales 10,000 miles away. An earthquake on one side of the world sends sound through the Sofar Channel that can be detected hours later on the other side, the baleen whales, those great, gentle, filter-feeding giants of the ocean, the blue whale, the fin whale, the humpback, have calls that are tuned precisely to the frequencies that travel best within the Sofar Channel. The blue whale produces calls at frequencies as low as 10 to 40 hertz, below the lower limit of human hearing. These are among the loudest sounds produced by any animal on Earth, and they travel through the Sofar Channel with astonishing efficiency. A blue whale calling in the central Atlantic may be heard by another blue whale in the far North Atlantic, thousands of kilometers away. For a long time, scientists assumed that the deep ocean was essentially quiet below the Sofar Channel. In the truly deep zones, where pressure has increased the speed of sound beyond the channel's influence, but research has revealed that the deep ocean has its own complex acoustic environment. The sounds of the mid-ocean ridge, the gentle cracking of new rock cooling against cold seawater, the hiss and rumble of hydrothermal vents, the low-frequency groan of the seafloor spreading, all of these reach the deep water and propagate through it, creating a constant, very low, very subtle acoustic backdrop to life in the abyss, in the deep ocean, where light is absent, sound and other non-visual senses take on an importance they cannot have in the sunlit world. The animals of the deep have evolved extraordinary sensory capabilities to compensate for the loss of sight. The lateral line is a sensory system possessed by all fish, but one that becomes particularly important in the dark. Running along both sides of a fish's body, from just behind the head to the base of the tail, the lateral line is a canal filled with fluid and lined with sensory cells called neuromasts. Each neuromast contains tiny hair-like projections that move when the fluid in the canal shifts, and these movements are detected by the sensory cells and transmitted as nerve signals to the fish's brain. The lateral line detects the movement of water, very subtle movement. The pressure waves created by another animal swimming nearby, the slight turbulence left in the water behind a paddle, passing creature, the disruption in the flow of current caused by an obstacle or a food particle. A fish with a functioning lateral line has a kind of spatial awareness that extends beyond its own body, a bubble of tactile sensitivity in the water around it that tells it what is nearby, even in total darkness, for deep-sea fish living in the abyssal zone, where there is no light of any kind. The lateral line may be the primary means of detecting both prey and predators. Some deep-sea fish have lateral line systems of unusual sensitivity, with more or larger neuromasts than their shallow water relatives, tuned to detect the faintest possible movements in the water around them. The tripod fish, standing on the abyssal plain on its fin stilts, extends its pectoral fins to either side, not merely as a posture, but as an extension of its lateral line sensing, using the elongated fins like antennae to detect the pressure waves created by small animals approaching in the current. Electroreception is another extraordinary sense found in sharks and some other fish. Every living cell produces a small electrical field, a consequence of the chemical processes of life. These fields are extraordinarily faint, far too faint for any human instrument to detect without specialized equipment. But sharks and some deep-sea relatives possess organs called ampullae of Lorenzini, small jelly-filled canals opening in pores on the animal's skin that can detect electrical fields of almost incomprehensible faintness. Sharks can detect fields as weak as 5 billionths of a volt per centimeter of water. In practical terms, this means a shark can detect the electrical field produced by the muscle contractions of a flatfish buried beneath the sand, or by a small crustacean resting motionless in the sediment, with no visual, acoustic, or chemical signal available at all. Some deep-sea animals navigate by chemical sensing, following gradients of dissolved compounds in the water, the way a scent trail might be followed in air. The ocean is full of dissolved chemicals, many of them produced by living organisms, and many of them persisting in the water far from their source. A deep-sea isopod following a gradient of dissolved organic compounds through the dark water, is navigating as surely as a hound following a scent. The combination of all these non-visual senses, sound detection through the lateral line, and through specialized hearing organs, electroreception, chemoreception, pressure sensing, creates a picture of the deep ocean not as a dark, featureless void, but as a richly sensed environment, a world full of information encoded in pressure and chemistry and electricity and the movement of water rather than in light. The animals of the deep read this world fluently. They have been reading it for millions of years, and the Sofar Channel sings quietly beneath them, carrying the sounds of whales and earthquakes and the slow grinding of tectonic plates around the whole planet. A long, low, continuous music that has been playing in the deep ocean for as long as the ocean has existed. Let it play now in the background of your awareness, very low, very slow, a deep humming below the threshold of hearing, the ocean breathing, the planet alive, and you resting on the surface of all of that slow sound, drifting gently, very quiet and very still. We know the shape of the deep ocean floor less well than we know the surface of the moon. That is not a figure of speech. It is a straightforward statement of fact. Detailed maps of the lunar surface exist that show features just a few meters across. Detailed maps of Mars reveal individual boulders and gullies in extraordinary clarity. But the floor of our own ocean, the largest landscape on our own planet, remains largely unmapped at any meaningful resolution. As of the most recent global assessments, around 27 to 28% of the world's seafloor has been mapped to modern standards. The remaining 72 or 73% is known only in the very broadest outline, or not at all. This is not for lack of trying. Mapping the deep seafloor is genuinely one of the most technically challenging tasks in all of science. And yet, the tools scientists have developed to do it, and the slow, patient progress they have made, are a story of ingenuity and persistence that deserves to be told gently and fully. The fundamental challenge is this: light does not travel far in water. Unlike on land, where we can photograph landscapes from satellites and aircraft using reflected sunlight, the deep ocean floor cannot be imaged from above with light. The water absorbs it long before it reaches the bottom. Instead, scientists use sound. Sound, as we discussed in our previous section, travels well through water. Mapping instruments send pulses of sound downward from a ship at the surface and listen for the echo that returns from the seafloor below by measuring very precisely how long the echo takes to return, and knowing how fast sound travels through the water at various depths. Scientists can calculate exactly how deep the seafloor is at that point. They map the seafloor by bouncing sound off it, one depth measurement at a time. The earliest ocean depth measurements were made with lead weights on lines, lowered over the side of a ship until they reached the bottom. This was slow work. A single depth measurement in very deep water could take hours. The first systematic measurements of ocean depth were made in the 19th century, and they revealed for the first time that the ocean was far deeper than anyone had imagined, and that the seafloor was not flat. The development of sonar, which uses sound pulses to measure depth, transformed deep-sea mapping. Early sonar systems used a single beam of sound sent straight downward from the ship. This gave a single depth measurement along the ship's track, a thin line of data across the vast ocean. To map an area properly with single beam sonar, a ship would need to make hundreds of closely spaced parallel passes, a process that would take years for even a small region of the seafloor. The development of multi-beam sonar changed everything. Instead of sending a single pulse directly downward, a multi-beam sonar system sends out a fan of sound pulses simultaneously, spreading outward to either side of the ship's track. Each pulse in the fan strikes the seafloor at a slightly different angle and returns with information about the depth and texture of the seafloor at a different point across a wide swath. A single pass by a ship equipped with multi-beam sonar can map a corridor of seafloor hundreds of meters wide, building up a detailed three-dimensional picture of the bottom topography as the ship moves forward. Modern multi-beam sonar systems mounted on research ships can map swaths of seafloor up to 30 or 40 kilometers wide in a single pass in very deep water. The data they collect is extraordinarily detailed, resolving features just a few meters across in ideal conditions. The maps produced look like the topographic maps of mountain ranges, with ridges and valleys and plains rendered in precise elevation data, colored by depth from shallow blues to deep purples, a landscape revealed in sound, but even with multi-beam sonar, mapping the entire ocean floor at high resolution is an enormous undertaking. The ocean covers more than 360 million square kilometers. A single research vessel working continuously might map around 200 to 500 square kilometers of seafloor per hour. At that rate, mapping the entire ocean would take centuries with a single ship. This is why an international initiative called Seabed 2030 was established, with the goal of producing a complete, high-resolution map of the entire ocean floor by the year 2030. It coordinates the efforts of research vessels from dozens of countries, collects and standardizes mapping data from commercial shipping vessels and naval ships equipped with sonar, and organizes the world's ocean mapping community around a common goal. As of early 2026, around 27 to 28% of the global seafloor has been mapped to modern standards. Progress is steady, but reaching full coverage by 2030 will require a significant acceleration of effort for the very deepest parts of the ocean, where the water column is so thick that even multi-beam sonar pulses sent from a surface ship are spread and weakened by the time they reach the bottom. A different approach is needed. Autonomous underwater vehicles, robotic submarines that carry their own sonar systems, can be sent down close to the seafloor, where their sonar maps the bottom, far greater precision than any surface-mounted system could achieve. These vehicles travel slowly along programmed paths just a few hundred meters above the seafloor, building up extremely detailed maps of small areas. Some of the most spectacular recent discoveries in seafloor mapping have come from these autonomous vehicles. Detailed surveys of mid-ocean ridge crests have revealed volcanic structures, fault systems, and hydrothermal vent fields that were completely unknown before the surveys were conducted. The surveys of seamounts have revealed their complex, varied topography, with steep cliffs, flat summit plateaus, and deep volcanic craters. Maps of deep-sea trench floors have shown them to be not simple, uniform trenches, but complex landscapes with their own ridges, scarps, and sediment-filled valleys. Satellite technology has also played a role in ocean mapping, though not in the way you might expect. Satellites cannot see the seafloor directly, but the gravitational attraction of large underwater features, seamounts, ridges, and deep trenches slightly distorts the shape of the sea surface above them. The ocean surface bulges very slightly, by just a centimeter or two, over a large seamount, pulled upward by the extra gravitational pull of the dense rock below. Very precise satellite measurements of the ocean surface shape can therefore reveal the broad outlines of major underwater features, giving a low-resolution picture of the seafloor, even in areas that have never been visited by a ship or a sonar system. This satellite gravity method has given scientists a global picture of the deep ocean floor in broad strokes, revealing the overall pattern of mid-ocean ridges, ocean trenches, and major seamount chains all over the world. It was this kind of satellite mapping that first gave scientists a comprehensive view of the global structure of the ocean floor, confirming and extending the picture built up over decades of ship-based measurements. The act of mapping the deep seafloor is, in some ways, a profoundly patient and humble endeavor. A research ship moving at 10 or 15 kilometers per hour, sweeping its sonar fan back and forth, across an ocean that has existed for hundreds of millions of years, the data accumulating slowly, track by track, year by year, building up a picture of a landscape that has never been seen by any human eye, and that is larger than all the continents combined. Every new map reveals new things. Every survey of a previously unmapped seamount finds species that have never been recorded, geological features that challenge existing models, ecosystems that no one suspected were there. The deep seafloor is so large and so unexplored that even a brief survey of a small area, a few square kilometers of previously uncharted bottom, routinely produces discoveries that would occupy scientists for years to study and describe. The ocean floor has been there all along. Ancient, dark, patient, waiting to be known. And the maps are slowly, carefully filling in the blank spaces, one sonar track at a time. It is slow work, but slow is what the deep ocean has always asked of us. And in the slow, careful sweep of the sonar beam across the dark floor below, in the patient accumulation of depth measurements, line by line, there is a kind of meditation, a quiet attention to something vast and still and largely unknown, like drifting, like dreaming, like the long, slow movement of your own breath right now, measuring the quiet landscape of this dark and gentle night. To visit the deep ocean in person, you must build a vessel capable of the impossible. It must withstand pressures that would crush a steel drum flat. It must keep a human being warm and supplied with breathable air at temperatures just above freezing. It must carry enough power to run its motors, its lights, its instruments, and its life support systems for many hours. It must be able to sink to the seafloor and return reliably and safely to the surface, and it must be small enough and maneuverable enough to navigate the tight, irregular terrain of the deep seafloor, hovering above a hydrothermal vent, or approaching a strange animal without disturbing it. Building such a vessel is one of the great engineering achievements of the 20th century, and the history of deep ocean exploration is inseparable from the history of the remarkable machines built to carry science into the dark. The story of human-occupied deep submersibles begins with a Swiss physicist named August Pickard, who designed and built a vessel he called a bathyscaphe in the years following the Second World War. The bathyscaphe was not sleek or elegant. It was a large steel sphere built to resist pressure, suspended beneath a huge float filled with gasoline, which is lighter than water, providing the buoyancy to carry the heavy steel sphere downward and allow it to return to the surface. In 1960, August Pickard's son, Jacques Pickard, and a United States Navy officer named Don Walsh descended in the bathyscaphe, Trieste, to the floor of the Challenger Deep in the Mariana Trench, reaching a depth of nearly 11,000 meters. It was the deepest dive in history. 2 human beings sitting in a sphere of steel at the bottom of the world. They remained on the bottom for 20 minutes, long enough to observe that even at the greatest depth on Earth, life was present. A small flatfish, they reported, resting on the seafloor. Modern deep submersibles are very different from the Trieste. The most famous research submersible in history is almost certainly Alvin, a vessel operated by the Woods Hole Oceanographic Institution in Massachusetts. Alvin was commissioned in 1964, and it has been diving ever since, making more than 5,200 dives over its 60 years of service. It carries a pilot and 2 scientists in a titanium sphere just 2 meters in diameter, and it has been upgraded many times over the decades, extending its maximum dive depth. After its most recent major overhaul, Alvin can reach depths of around 6,000 meters, allowing it to access approximately 98% of the ocean floor. Alvin's history is remarkable. It was Alvin that first directly observed and sampled the hydrothermal vents of the Galapagos Rift in 1977. That discovery, which changed the scientific understanding of life on Earth. It was Alvin that explored the wreck of the RMS Titanic in 1986, descending to the 4-kilometer deep resting place of the great ship and bringing back the first close-up images of the wreck in its deep-sea setting. It has collected thousands of biological and geological samples, planted and retrieved instruments on the seafloor, and carried scientists to places they could not otherwise have reached for 6 decades of uninterrupted research. Descending in Alvin is a slow experience. The submersible sinks at a rate of roughly 30 meters per minute, meaning a dive to 4,000 meters takes over 2 hours just for the descent. The occupants sit in a sphere just large enough to be comfortable, with small viewport windows of borosilicate glass, through which they watch the world outside darken and cool as the depth increases. The blue light of the upper water column dims slowly to nothing. The darkness becomes complete, and then, gradually, the lights of the submersible begin to reveal the seafloor rising toward them from below. The experience is described by those who have made the dive as profoundly quiet. The hum of the motors, the soft sound of the life support systems, and outside the viewports, total silence and total darkness, until the submersible's own lights illuminate the extraordinary world below. But human-occupied submersibles, remarkable as they are, have significant limitations. They are expensive to operate. They can only carry 2 or 3 people. Each dive lasts a limited number of hours before the occupants must return to the surface. They can only be in one place at a time, and they are vulnerable in ways that unmanned vehicles are not to the consequences of any failure deep in the ocean. This is why the development of remotely operated vehicles, commonly called ROVs, has transformed deep ocean research. An ROV is an unoccupied vehicle controlled by operators aboard a ship at the surface via a long cable that carries power down to the vehicle and transmits video and data back up. The operators sit at a console watching high-definition video from the ROV's cameras on screens in front of them, and controlling the vehicle's movements with joysticks and buttons. It is very real sense, like playing an extremely consequential video game with a vehicle worth millions of dollars moving through the deep ocean in response to the operator's inputs. ROVs can be much larger and carry more equipment than a human-occupied submersible because they do not need to provide life support for any human passengers. They can carry multiple cameras, sonar systems, sampling tools, and scientific instruments. They can hover in one position for as long as needed. They can work at depths that no human-occupied vehicle has ever reached. And if something goes wrong, the ROV can be sacrificed without any risk to human life. Though of course the goal is always to bring it back. The manipulator arms of a large research ROV are among the most delicate and precise tools in all of deep-sea science. These articulated arms, controlled by the operator at the surface, can pick up a single fragile glass sponge from the seafloor without damaging it, or place a small sensor on a hydrothermal vent chimney with millimeter precision, or collect a sample of sediment in a carefully labeled container. Watching video footage of an ROV manipulator arm working at 4,000 meters depth, its movements translated from a console thousands of meters above through a cable thinner than a garden hose, is to watch a remarkable marriage of technology and patience. Autonomous underwater vehicles, or AUVs, take the idea of unmanned deep-sea exploration one step further. Unlike ROVs, which remain tethered to the surface ship and under continuous human control, AUVs operate independently. They are programmed before launch with a mission, a series of waypoints to visit, depths to sample, measurements to make, and they carry out that mission entirely on their own, without any communication with the surface. When the mission is complete, they return to a pre-programmed location where they can be recovered. AUVs are particularly valuable for large-scale surveys. A research ship can deploy an AUV, then move on to other work, while the AUV spends hours or days surveying a large area of seafloor, collecting sonar data, taking water samples, measuring temperature and chemistry at various depths. The AUV works quietly and continuously, a patient robot going about its programmed task, while the scientists aboard the ship sleep, eat, and work on other things. Some AUVs are designed not to swim, but to glide. Ocean gliders are slender, torpedo-shaped vehicles with no propellers. Instead, they change their buoyancy by pumping oil between an internal reservoir and an external bladder. When the bladder inflates and the vehicle becomes more buoyant, it rises. When the bladder deflates and the vehicle becomes less buoyant, it sinks. Wings on the vehicle convert this vertical motion into forward movement by cycling up and down through the water column in a long, shallow sawtooth path. A glider can travel enormous distances on very little energy. Some ocean gliders have been at sea continuously for months, quietly sampling the ocean as they travel, sending data back via satellite whenever they surface. All of these vehicles, the crewed submersibles, the tethered ROVs, the autonomous AUVs, the slow gliders, are instruments of patience. Patience in their design, which takes years, patience in their operation, which unfolds over hours and days and months. Patience in their purpose, which is to understand a world that took 4 billion years to reach its current form, and that will not reveal itself quickly to any investigation that is not willing to go slowly, to look carefully, and to wait. The deep ocean has always rewarded patience, and the machines we have built to explore it have had to learn that lesson too. Think of them now, quietly, moving through the dark, an ROV hovering above a coral garden at 3,000 meters. Its lights illuminating a small, still world while its cameras watch. An AUV gliding in slow zigzags through the water column, sampling and measuring and recording somewhere below them all. The seafloor, vast and dark, and full of things not yet known. And above them, connected by a cable or a radio signal, or simply by intention, human beings watching screens, taking notes, asking questions of the deep, very quietly, very patiently, one dive at a time. deep ocean, there are ghosts. Not in any frightening sense, not anything alarming, just the quiet, still remnants of the human world, settled on the seafloor, slowly becoming part of it. Ships that set out from ports in sunlight and never returned. Vessels that crossed storms and icebergs and wars and accidents, and finally came to rest on the cold seafloor, far below the surface world they once moved through. They lie there now in the dark, gradually being reclaimed, becoming habitats, becoming history preserved in cold salt water, becoming part of the deep in a way that is, when you think about it slowly and gently, rather peaceful. There are estimated to be hundreds of thousands of shipwrecks on the ocean floor around the world. From ancient wooden vessels thousands of years old to 20th century ships of iron and steel, the seafloor is scattered with the artifacts of every era of human navigation. Many of them lie in shallow coastal waters, where they have long been found and studied, and in many cases plundered. But a great many lie in the deep ocean, far from the reach of any diver, in the cold dark, at hundreds or thousands of meters depth. The wreck of the RMS Titanic is the most famous deep-water shipwreck in the world, and it is in some ways the wreck that transformed public and scientific awareness of what the deep ocean floor preserves. The Titanic sank on the night of the 14th and 15th of April 1912 after striking an iceberg in the North Atlantic during her maiden voyage from Southampton to New York. More than 1,500 people died in the disaster. For over 70 years, the ship lay on the seafloor, undiscovered, at a depth of around 3,800 meters, approximately 2.5 miles below the surface. In 1985, a joint expedition by the Woods Hole Oceanographic Institution and the French Research Institute, IFREMER, using a deep-towed camera system, located the wreck. The images that came back from the seafloor were extraordinary. The ship lay in two main pieces, the bow section and the stern section, separated by about 600 meters. The bow, the forward section of the ship, was remarkably intact. It rested on the seafloor with its prow pointed downward at a slight angle, its railing still in place, its anchor still stowed, covered in long, rust-brown formations called rusticles, dangling like long, dripping stalactites from every horizontal surface. It was unmistakably the Titanic, vast and still and silent in the dark. The stern section, which had twisted and buckled catastrophically as the ship broke apart on the surface during the sinking, was in far worse condition. Its structure collapsed and deformed between the two sections across 600 meters of seafloor. A debris field stretched, scattered with the artifacts of the lives that had been lived aboard the ship. China, silverware, shoes, personal items, the remnants of a world that had ceased to exist on the surface of the ocean 112 years ago. The rusticles that cover the Titanic's iron and steel hull are not simply rust. They are biological structures, metal-eating bacteria, including a species named Halomonas titanici in honor of the ship, have colonized the hull over the decades. These bacteria consume iron, extracting energy from its oxidation, and in doing so, they produce the long, rust-colored formations that hang from the hull like stalactites in a cave. The rusticles are not inert. They are living, metabolically active structures, teeming with microbial communities that are slowly, steadily consuming the iron of the ship. Scientists who have monitored the wreck over multiple visits have documented its accelerating deterioration. Sections of the hull that were intact in 1986 have collapsed in the decades since. The captain's bathtub, visible in early photographs, has now fallen into the surrounding sediment as the deck above it gave way. The cold water and the absence of light slow the decomposition, but they cannot stop it. Eventually, over centuries, the Titanic will be completely consumed, its iron reduced by bacteria to rust, its remaining structure collapsing into the sediment, until what remains is only the materials that bacteria cannot easily digest. The ship is already 3/4 of a century, more than a century old, in its deep resting place. in another few centuries it will be gone. But while it lasts, it is remarkable, and it is not lifeless. Far from it, shipwrecks in the deep ocean, regardless of their age or their material, become habitats. They provide hard substrate in an environment where hard surfaces are rare. The soft sediment of the abyssal plain is not easily colonized by animals that need to anchor themselves. Animals like corals and sponges and crinoids, which need a firm attachment point. A shipwreck provides exactly that. Harder surfaces, irregular topography, shelter from the slight currents of the deep, and a supply of nutrients released by the slow decomposition of the ship's organic materials. The wood of the decks, the paint, the rubber, the rope, the fabric, within years of a ship sinking to the deep sea floor, it begins to be colonized. Bacterial biofilms form first, covering every surface with a thin, sticky layer of microbial life. Then larger organisms arrive, drawn by the biofilm, or simply by the hard surface. Corals, anemones, sponges, worms, small crustaceans, fish seeking shelter. Over decades and centuries, a shipwreck accumulates an increasingly complex community, becoming a deep-sea reef, an island of life in the otherwise sparse landscape of the abyssal plain. Wooden shipwrecks follow a different and particularly interesting trajectory. Older wooden vessels, of which many thousands rest on the deep seafloor from centuries of sail-powered trade, exploration, and warfare, are colonized by wood-boring organisms and wood-decomposing bacteria and fungi. The wood of a sunken vessel, submerged in the cold, oxygen-poor water of the deep ocean, decomposes far more slowly than wood on land, where oxygen and warmth accelerate the process. A wooden ship on the deep seafloor may persist for centuries, slowly being consumed from within by the organisms that specialize in digesting the complex cellulose and lignin molecules that make up its timber. As the wood is consumed, it releases organic compounds into the water and sediment around it, creating a plume of enrichment that extends outward from the wreck for hundreds of meters. community, different from both the wreck community and the surrounding ambient seafloor community. Each wooden shipwreck creates its own unique chemical and biological signature in the sediment around it. A fingerprint of decomposition and enrichment that researchers can detect and study even in the sediment layers long after the wood itself is gone. Among the most poignant deep-sea shipwrecks are those from the 2 world wars. The hundreds of naval vessels and merchant ships sunk by submarines and aircraft and mines in both the Atlantic and the Pacific. Many of these ships carried not only cargo, but human beings who died with them. And their wrecks are therefore protected by law as war graves in many countries. They lie in the deep ocean now, decades, and in some cases more than a century later, slowly becoming part of the seafloor ecology. Their stories preserved both in the archaeological record and in the living communities that have established themselves in and around the rusting hulls. There is something deeply human about the fact that our artifacts, our ships, our tools, our belongings find their way to the deep ocean and are received there, not rejected, not inert, but incorporated, colonized, transformed. The deep ocean takes what we send to it and makes something of it. A habitat, a reef, a chemical enrichment zone, a community of life where before there was only soft sediment. The deep ocean does not distinguish between what falls naturally. The whale carcasses, the marine snow, the fallen seamount rubble, and what falls as a consequence of human history. It accepts everything. It processes everything, slowly, patiently, in the dark. It makes something living from everything that arrives. Rest with that thought for a moment. The deep is not harsh. It is not indifferent. It is simply vast and patient and generous in its quiet way with whatever it receives. Your thoughts are drifting down now, one by one, settling gently into the quiet dark below, and the deep receives them softly, without judgment. The deep ocean is doing something extraordinary right now, at this very moment, as you rest. It is protecting you, not in a dramatic way, not in any foresee, but quietly, persistently, on a planetary scale. The deep ocean is absorbing the consequences of the changes humanity has made to the atmosphere, slowing those changes down, buying time. It has been doing this since the very beginning of the industrial age, and it continues to do it now, in the cold and the dark, far below any surface anyone will ever see. The ocean has absorbed more than 90% of the excess heat generated by the increase in greenhouse gases since the Industrial Revolution began. Not 90% of the heat trapped near the surface, not 90% of the heat in the atmosphere. 90% of all the additional heat energy that the enhanced greenhouse effect has added to the entire Earth system. The vast majority of global warming, in the most literal physical sense, has happened in the ocean, not in the atmosphere. Think about what that means. If the ocean had not absorbed that heat, if all of it had remained in the atmosphere, global average air temperatures would already be far higher than they are today. Scientists have calculated that without the ocean as a heat buffer, the average surface temperature of the Earth could have reached 50 degrees Celsius or more. The ocean's capacity to absorb and store heat has been the single most powerful moderating force on the pace of surface warming. It has, in a very real sense, been absorbing the climate crisis on our behalf. It has also been absorbing carbon dioxide. Since the 1980s, the ocean has absorbed around 25 to 30% of all the carbon dioxide emitted by human activities, from burning fossil fuels, from deforestation, from industry. The ocean is the largest active carbon reservoir on the planet, storing around 38,000 billion tons of carbon in total. That is 28 times more carbon than is stored in all land vegetation and the entire atmosphere combined. The mechanisms by which the ocean absorbs and stores this carbon are the same ones we have visited on our journey tonight. The physical pump, cold surface water at the poles, dense with dissolved carbon dioxide, absorbed directly from the atmosphere, sinks through the process of thermohaline circulation and carries that carbon down into the deep ocean, where it is stored far from the atmosphere for centuries or longer. Every cubic meter of cold, sinking water near the poles carries a small cargo of dissolved carbon down into the abyss, withdrawing it from the surface cycle and keeping it stored in the deep. The biological pump, phytoplankton at the surface, take up carbon dioxide through photosynthesis, incorporating it into their tiny bodies. They are grazed, they die, they become marine snow, and they sink. The carbon they captured at the surface travels with them downward through the water column. Some fraction reaches the seafloor and is buried in the sediment, removed from circulation for thousands or millions of years. The biological pump transfers somewhere between 5 and 12 billion tons of carbon from the surface to the deep ocean every year. Without it, carbon dioxide concentrations in the atmosphere would be significantly higher than they are today. The deep ocean is also where heat is redistributed around the planet. The thermohaline circulation, that great slow conveyor belt of ocean water, driven by the sinking of cold, salty water at the poles, transports not just water and carbon, but heat. Warm water from the tropics flows toward the poles at the surface, releasing its heat to the atmosphere along the way, and warming the climates of the lands it passes. At the poles, it cools and sinks, and flows as cold, deep water back toward the tropics along the ocean floor. This redistribution of heat between the tropics and the poles is one of the fundamental processes that makes large parts of the Earth habitable. The climate of northwestern Europe, including Britain, Scandinavia, and the countries around the North Atlantic, is significantly warmer than it would otherwise be for its latitude, largely because of the heat transported northward by the Atlantic branch of the thermohaline circulation. The winters of London are mild compared to those of other cities at similar latitudes in Canada or Siberia, in large part because of the warmth delivered by the ocean current system. The Southern Ocean, that vast ring of water encircling Antarctica, deserves particular recognition in this story. although it covers only about 25% of the global ocean surface, it has absorbed around 50% of the excess heat added to the ocean since the year 2005, and around 40% of the carbon dioxide absorbed by the global ocean. The extreme cold of the Antarctic surface waters, the powerful winds that drive vigorous mixing, and the structure of the deep circulation in the Southern Ocean make it an extraordinarily efficient absorber of both heat and carbon. It is one of the most important climate regulators on our planet. The sediments of the deep seafloor are also a long-term carbon archive of extraordinary importance. The white cliffs of Dover are made largely of the accumulated shells of microscopic plankton that settled to an ancient seafloor over millions of years. Their carbonate shells locking up carbon that had been absorbed from an ancient atmosphere. Similar deposits exist across the floors of all the world's oceans. Thick layers of carbonate-rich sediment recording millions of years of ocean chemistry and atmospheric carbon dioxide concentrations. Scientists drill into these sediments to read the record they contain, extracting cores of sediment that carry in their chemistry a detailed account of every climate change our planet has experienced over tens and hundreds of millions of years. This record tells us that the climate of the Earth has changed dramatically many times in its history, that ice ages and warm periods have alternated over thousands and millions of years, that the ocean has been a key player in every one of these transitions, absorbing and releasing carbon, transporting heat, driving changes in atmospheric chemistry that in turn drove changes in surface temperature and ice cover. The deep ocean is not just a passive record of climate history. It has been an active participant in shaping that history, and it continues to shape it now. The relationship between the deep ocean and the climate is one of extraordinary intimacy and mutual dependence. The climate shapes the ocean, determining where cold water sinks, how strong the circulation is, how much carbon the surface water can absorb. And the ocean shapes the climate redistributing heat, sequestering carbon, moderating the pace of warming. They are locked together in a slow, planetary embrace that has been going on for as long as the ocean has existed. When we think of the deep ocean as something remote and separate from our daily lives, we are missing something fundamental. The deep ocean is not separate from us. It is inseparable from us. Every breath we take is influenced by the chemistry the ocean regulates. Every rainstorm, every river, every snowfall traces its water back through a cycle that passes through the ocean. The warmth of the air around us reflects, in part, what the ocean has chosen to hold and what it has chosen to release. The ocean holds the world in balance, and it does this quietly, invisibly, in the cold and the dark, without any recognition or acknowledgement, simply because that is what it does, what it has always done, what it will continue to do for as long as it exists. Rest in the knowledge of that now. The deep ocean is beneath everything, holding everything, regulating everything, patient and vast, and doing its quiet work. And you, resting now, are part of that same world, breathing the air the ocean helps to keep breathable. Warmed by the heat the ocean helps to distribute. Alive in the balance the ocean helps to maintain. You are held by the deep right now. The seafloor is not still. It gives every appearance of stillness. When we think of the abyssal plain, we picture cold sediment, very slow currents, the gentle drift of marine snow. Nothing moves quickly down there. Nothing rushes, and in terms of the pace of biological life, that picture is accurate. But beneath the soft sediment, beneath the layers of ancient carbonate and clay, and the remains of billions of generations of plankton, the rock itself is in motion. The planet is alive below the seafloor, and the evidence of its restlessness shapes everything above it. Around 80% of all the volcanic eruptions on Earth take place underwater. Not on land, not in the dramatic explosions of volcanoes that fill the sky with ash and lava, visible from hundreds of kilometers away. In the ocean, quietly, mostly unseen, deep beneath the surface, in the cold dark at the crest of the mid-ocean ridge system, the Earth is constantly making new rock. We visited the mid-ocean ridge briefly on our journey across the seafloor. Early in tonight's exploration. But let us return to it now and think about it in more depth, because it is one of the most extraordinary geological phenomena on our planet, and its activity shapes everything we have discussed since the mid-ocean ridge is the longest chain of volcanoes on Earth, stretching nearly 65,000 kilometers through every ocean basin. It marks the boundaries between the great tectonic plates that make up the Earth's crust. At the ridge crest, two plates are slowly moving apart, pulled by convection currents deep in the Earth's mantle. As they separate, the gap between them is filled from below by molten rock, magma rising from the mantle. This magma reaches the seafloor at the ridge crest, erupting as lava into the cold, deep water. The encounter between very hot lava and very cold seawater is remarkable. On land, a lava flow cools relatively slowly, spreading across the landscape in thick, glowing sheets. But at the deep seafloor, where the water temperature is just above freezing and the pressure is hundreds of times the surface pressure, lava cools almost instantly when it contacts the seawater. The outer surface of the lava solidifies in seconds, forming a thin skin of glassy rock. But inside that skin, the lava is still molten and still flowing. As it flows forward, it inflates the glassy skin until the skin cracks, and a new lobe of lava pushes out through the crack, and in turn solidifies on its outer surface. The result is a landscape of rounded, pillow-shaped formations called pillow lava, stacked upon one another in great mounds, covering the ridge crest in shapes that look, when illuminated by the lights of a research submersible, like enormous gray-black bolsters, or the smooth, rounded boulders of a riverbed. This process of seafloor spreading, the continuous creation of new oceanic crust at the ridge crest, and its slow movement outward on either side, is not fast. The rate at which the plates move apart varies from ridge to ridge. The mid-Atlantic ridge, the slow-spreading ridge that runs down the center of the Atlantic Ocean separates at a rate of about 2 to 3 centimeters per year. The East Pacific Rise, a faster spreading ridge in the Pacific, separates at rates of up to 15 centimeters per year by geological standards. These are not trivial speeds. Over millions of years, centimeters per year accumulate into hundreds of kilometers of new seafloor. The Atlantic Ocean is widening right now as you rest. The floor of the Atlantic is spreading millimeter by millimeter, week by week, because new rock is being made at the mid-Atlantic ridge, and the old rock is being pushed outward. North America and Europe are moving apart. They have been moving apart for about 180 million years, since the supercontinent Pangaea began to break up, and the Atlantic Ocean first opened as a narrow seaway between the separating landmasses. Every year, the distance between them increases by about the thickness of a finger. It is a movement so slow as to be completely imperceptible in a human lifetime. And yet, over geological time, it has produced one of the world's great ocean basins at the far edges of the ocean basins, where the old, cold, dense oceanic crust reaches the margins of the continents. It meets another plate of rock, and because old oceanic crust is denser than continental crust, it bends downward and slides beneath the continental plate in a process called subduction. The descending slab of oceanic rock carries with it water, carbon, and other volatile compounds absorbed during its long journey across the ocean floor. As this slab descends into the hot mantle, the water and volatiles are driven off by the increasing temperature and pressure, rising into the mantle wedge above the descending slab and triggering melting. The resulting magma rises through the overriding plate, erupting in chains of volcanoes along the continents, or island arcs above the subduction zone. The subduction process also generates earthquakes. The descending slab of oceanic rock does not slide smoothly into the mantle. It sticks against the overriding plate, and the strain builds over decades or centuries until until the two plates suddenly lurch past one another, releasing enormous amounts of stored energy as an earthquake. The Great Subduction Zone earthquakes, some of the most powerful ever recorded, occur at the margins of the Pacific Ocean, where old oceanic plates are descending beneath the surrounding continents and island chains. The 2004 Indian Ocean earthquake, which triggered the devastating Indian Ocean tsunami, occurred on a subduction zone where the Indian Ocean plate was descending beneath the island of Sumatra. These processes, the spreading of the seafloor at the ridges, the subduction of old crust at the trenches, the building of volcanoes, and the generation of earthquakes are not separate events. They are part of a single, continuous cycle called plate tectonics, the slow movement and recycling of the Earth's outermost rocky shell. It is a cycle that operates on timescales of tens of millions of years, far beyond any human perspective, driven by the slow convection of the hot mantle rock beneath the crust. The seafloor at the mid-ocean ridge is the youngest crust on Earth. The rock just centimeters from the ridge crest may have been created within the last few thousand years. The rock further from the ridge is progressively older, recording in its magnetic signature the history of the Earth's magnetic field over millions of years. And the oldest oceanic crust, found at the far edges of the ocean basins, far from any ridge, is around 200 million years old before it finally descends into a subduction zone and is recycled back into the mantle. On land, the oldest rocks on Earth are over 4 billion years old. But on the seafloor, nothing is older than around 200 million years, because all the older oceanic crust has long since been recycled through subduction. The seafloor is perpetually young, perpetually renewing itself. The oldest part of the ocean floor is still younger than the oldest dinosaur fossil. There are places on the mid-ocean ridge where the seafloor spreading is particularly active, where magma chambers are relatively shallow, and the ridge crest is volcanically fresh and vigorous. Scientists monitoring these areas with hydrophone arrays, networks of underwater microphones, regularly detect the characteristic sounds of underwater eruptions. A long, low rumble, quite different from the sharp crack of an earthquake. As lava breaks through the seafloor and pours into the cold water, these eruptions are detected in real time, and ships and submersibles are sometimes dispatched to investigate within days, arriving to find the new lava still warm, its glassy surface unstained by the reddish iron oxides that will coat it within months. It is extraordinary to think that the floor of the ocean is being remade continuously, that the rock beneath every ocean on Earth is moving, spreading, cooling, aging, and eventually descending back into the mantle, that the very substrate of the deep, on which all the communities we have discussed tonight are living, is itself in motion, part of a planetary process of creation and destruction that has been running since the earth was young. The seafloor is restless, but its restlessness is very slow. Slow enough that every creature living on it, every coral and sponge and brittle star and cold seep mussel, lives out its entire life without perceiving any movement at all. The restlessness of the earth beneath is as invisible as the turning of the planet. Real, constant, immense, and utterly imperceptible to anything resting quietly on the surface of it. As you are resting quietly now, the earth is moving beneath you, very, very slowly, and you cannot feel it at all. Every expedition into the deep ocean finds something new. Not occasionally, not rarely. Every single time scientists send a submersible or a remotely operated vehicle into unexplored deep water, they encounter animals that have never been seen before, species that have never been described, creatures that have no name and no place in any catalog of the living world. The deep ocean is the last great unexplored wilderness on our planet, and it is yielding its secrets gradually, one dive at a time, to the patient attention of the scientists who go there to look between 2023 and 2025. An initiative called the Ocean Census, the world's largest collaborative effort to accelerate the discovery of marine life, announced the identification of over 866 new marine species, not 866 new specimens of known species. 866 species entirely unknown to science, found across 16 months of systematic surveying at depths ranging from just 1 meter below the surface all the way down to nearly 5,000 meters, species that had been living in the ocean for millions of years, going about their ancient lives, utterly unknown to human knowledge, until a camera or a sampling device happened to find them. Some of these discoveries are remarkable simply for what they are. A new species of isopod, a large crustacean related to the familiar pill bugs of garden soils, was found in deep water and given the informal name the Darth Vader isopod on account of the distinctive shape of its head, which bears a striking resemblance to the helmet of the famous fictional villain. It belongs to a group called Bathynomus, the giant isopods we mentioned earlier in our journey, and it is a significant new member of a group that scientists are still actively studying and cataloging. A new species of deep-sea squid named Mobadichia posidonii was described in 2025 from specimens collected in deep water. This was not merely a new species, but a new genus, a new branch on the tree of life, representing a lineage so different from its nearest relatives that it required an entirely new category to accommodate it. In 2026, a project to name 1,000 deep-sea animals by the year 2030 announced the description of 24 new crustacean species from deep ocean samples, adding to a list of deep-sea crustaceans that grows every year. Many of these creatures had been sitting in museum collections for years, collected on expeditions long past, waiting for a specialist with the time and knowledge to examine them carefully enough to recognize that they represented something new. New snailfish species have been described from the crushing depths of the Pacific trenches. Small, pale, soft-bodied creatures living at depths that no other vertebrate is known to tolerate. Each new snailfish found at extreme depth pushes the known limit of vertebrate a little further, asking us to revise our understanding of just how deep biology can reach in the Southern Ocean. Over 30 new deep-sea species have been verified from recent expeditions, including crustaceans, worms, corals, and fish. Each one adds a new dot to the map of deep ocean biodiversity, a map that is still largely blank, and that will remain so for decades to come. The pace of discovery is, if anything, accelerating. Better technology means faster, more comprehensive surveys. Better genetic analysis means that specimens that would once have been identified as known species are now routinely revealed by their DNA to be something new, a crab or a worm or a small fish that looks superficially identical to a known species turns out, when its genes are read, to be something entirely different, perhaps separated from its apparent twin by millions of years of independent evolution in different parts of the ocean. Scientists estimate that somewhere between 700,000 and 1 million species live in the ocean, excluding most microorganisms. At current rates of description, it will take many human lifetimes to catalog them all, and that estimate itself may be too low. Every time a new survey is conducted in a previously unsampled habitat, the number of unknown species encountered suggests that the true total may be far higher. There is a particular kind of discovery in the deep ocean that goes beyond the finding of a new species and reaches something closer to the profound. These are the discoveries of animals so different from anything previously known that they do not fit comfortably into any existing category of life. Animals whose body plans are so unusual, whose biology is so unexpected, that they require scientists to revise fundamental assumptions about what is possible. The discovery of the hydrothermal vent communities in 1977 was one such moment. The discovery of the barrel-eye fish's transparent dome was another. The discovery of chemosynthetic mussels at cold seeps, the first filmed observation of a live giant squid in its natural habitat. Each of these was not merely the finding of a new species, but the revelation of a new way of being alive, a new solution to the problem of existence that no one had imagined before it was found. The deep ocean has been producing these revelations continuously since scientists first began to visit it seriously. And the pace of revelation does not slow as we learn more. If anything, it increases, because each new discovery reveals new questions, new gaps in our understanding, new categories of thing we did not know. One of the most intriguing recurring discoveries in the deep ocean is the finding of animals thought to be extinct, or at least thought to have no living relatives in the modern ocean. The coelacanth, a fish with lobed fins that was thought to have been extinct for 65 million years, until a living specimen was found by a fisherman off the coast of South Africa in 1938, was eventually traced to populations living in deep water around the Comoro Islands, and later off the coast of Indonesia. It is a fish whose body plan has remained essentially unchanged for over 300 million years, a living document of an ancient ocean. The deep ocean shelters many such relics, animals whose lineages extend back into the deep past, and that have found in the stable, cold, slowly changing environment of the deep an existence that has required very little evolutionary modification for millions of years. The stalked crinoids that stand on the abyssal plain, extensions of their feeding arms into the slow current, are virtually indistinguishable from their Paleozoic ancestors of 450 million years ago. The nautilus, swimming in deep water in the western Pacific, carries a coiled shell and a body plan that has persisted for over 500 million years. The deep ocean is not only a place of new discovery, it is also a place of deep time, a refuge where ancient lineages persist in conditions stable enough to require very little change, where the evolutionary clock runs more slowly, where the past is still present and living when a new species is described from the deep ocean. It is usually given a name. The Latin binomial, the genus and species designation that locates it in the tree of life, and will identify it in scientific literature for as long as science persists. There is something quietly meaningful about this act. An animal that has lived in the deep ocean for millions of years, entirely unknown, suddenly receiving a name, being acknowledged, being placed in relation to everything else that lives, being made, in some small sense, part of our understanding of the world. The deep ocean is full of unnamed things, things that have existed for longer than our species has existed, living their ancient lives in the cold dark, carrying within their bodies a biology refined by millions of years of evolution. They do not need our names. They do not need our recognition. They are complete and whole and perfectly adapted without us. But when we name them, when we place them carefully in the catalog of living things and describe their morphology and their DNA and their habitat, we are doing something that only our species does. We are saying, you exist. We see you. You are part of the living world we share, and you matter. Let that thought settle gently now. All those unnamed things, living their quiet lives in the deep, and all the ones already named, filed in the pages of scientific journals, their long Latin names sitting in the dark like small lights, each one a revelation, each one a world. We have come a long way together tonight. From the sunlit surface, where the marine snow first begins its long descent, down through the twilight zone, where the last blue light fades, into the midnight zone and the abyssal plain, across the mid-ocean ridge, and down into the hadal trenches. We have visited hydrothermal vents and cold seeps, walked among stalked crinoids and glass sponges, drifted alongside giant squid and siphonophores, listened to the so far channel-carrying whale song across entire ocean basins, and rested in the knowledge that the deep ocean regulates our climate, our chemistry, our weather, and our air. And now, in this last full section of our journey, let us think gently but honestly about what the deep ocean faces, and why it matters that we understand it, and what it means to care for something so vast and so remote and so ancient. The deep ocean is not beyond our reach. obvious from what we have learned tonight. Submersibles reach it. ROVs explore it. The biological pump connects it to the surface. The thermohaline circulation connects it to every coastline on Earth. But the deep ocean's connectedness to our world also means that the things we do in our world reach down into the deep, changing it in ways both subtle and profound. Climate change is the deepest and most pervasive of these changes. The ocean, as we discussed in our climate section, has absorbed around 90% of the excess heat added to the Earth system by rising greenhouse gas concentrations. This has buffered the surface world from the full force of atmospheric warming. But it has not left the ocean unchanged. The deep ocean is warming. Slowly, because the deep is vast and the heat must work its way down through enormous volumes of water, but measurably, documentably, progressively. The bottom water in parts of the Atlantic and Pacific is warmer now than it was 50 years ago, and because the entire biology of the deep ocean, its metabolic rates, its reproductive cycles, its chemical balances, is calibrated to the stable cold temperatures that have prevailed for millions of years. Even small temperature changes can have effects that are difficult to predict and potentially impossible to reverse on any human timescale. Ocean acidification is another consequence of the ocean's role as carbon absorber. When carbon dioxide dissolves in seawater, it forms carbonic acid, lowering the ocean's pH and making it more acidic. This process is happening throughout the ocean, from the surface to the deep, though its effects are most advanced in the cold, deep water that holds the most dissolved carbon dioxide. For animals that build their bodies from calcium carbonate, the shellfish, the corals, the foraminifera, the pteropods. Acidification poses a direct threat. The more acidic the water, the more difficult and energetically costly it becomes to build and maintain carbonate structures. Cold water corals, those ancient, slow-growing deep-sea reefs that we visited earlier in our journey, are particularly vulnerable. Some cold water coral reefs are already experiencing conditions corrosive to their calcium carbonate skeletons. Bottom trawling is a fishing practice that has caused extensive damage to deep-sea habitats across many parts of the world's oceans. It involves dragging heavy weighted nets across the seafloor to catch fish and other commercially valuable species. And it is spectacularly non-selective. Everything in the path of the trawl is crushed, uprooted, or caught. Cold water coral reefs that took thousands of years to build are destroyed in minutes. Sponge communities, crinoid gardens, diverse communities of animals that took centuries to establish. All of it reduced to rubble in a single pass of a trawl net. Bottom trawling at deep-sea depths has been documented to depths of more than 2,000 meters in some areas, and its effects on deep-sea ecosystems are now recognized as among the most destructive of all human impacts on the ocean floor. Deep-sea mining is the newest, and in some respects, the most significant emerging threat. The deep seafloor contains enormous deposits of minerals, polymetallic nodules scattered across vast areas of the abyssal plain, rich in manganese, nickel, cobalt, and copper. Cobalt-rich crusts on seamount flanks, sulfide deposits at hydrothermal vent fields. These minerals are increasingly in demand for the manufacture of batteries, electronics, and the components of renewable energy technology. The pressure to mine them is growing. But the communities living on and around these mineral deposits, the abyssal fauna of the nodule fields, the unique ecosystems of the seamount crusts, the extraordinary vent communities, are precisely the communities most at risk from mining operations. Mining the nodule fields would require enormous machines moving across the abyssal plain, scooping up the nodules and generating vast plumes of sediment that would disperse across hundreds of square kilometers, settling on the seafloor and smothering the animals below. The nodules themselves, which take millions of years to form, cannot be replaced on any human timescale. And the animals that live on and around them, many of which exist nowhere else, would be gone. The fundamental challenge is that the deep ocean operates on timescales so far removed from human experience that damage, which seems modest by our standards, can be catastrophic by the deep ocean standards. A cold water coral reef destroyed by a single trawl pass took 500 years to build. A polymetallic nodule field eliminated by mining took 10 million years to accumulate. The deep ocean does not recover from damage quickly. It cannot. Its entire biology is calibrated to the slowness of the deep. This is why scientists and conservationists have argued strongly for the establishment of marine protected areas in the deep ocean, zones where extractive activities are prohibited, and the deep seafloor community is allowed to persist without human disturbance. Some such areas exist. The international community has negotiated frameworks for the management of deep-sea activities in international waters, but coverage remains far from adequate, and the pace of protection has not kept up with the pace of interest in deep-sea exploitation. There is also the matter of what we do not yet know. We have mapped less than 30% of the deep seafloor to modern standards. We have described a small fraction of its species. We have barely begun to understand the chemical processes its microbes carry out, the ecological relationships between its communities, the role of its biodiversity in maintaining the functioning of the deep ocean as a whole. We are contemplating large-scale industrial activity in an environment we do not yet understand, operating on timescales we cannot comprehend, affecting species we have not yet named, in ecosystems we have never fully surveyed. Scientists have consistently argued for a pause, for more time to understand the deep ocean before transforming it irreversibly. Not forever, not a permanent prohibition, just the time to know what is there, what it does, and what we would lose. Because the deep ocean does things for us that we cannot do for ourselves and cannot replace. It regulates our climate. It sequesters our carbon. It drives our ocean circulation. It produces, through its microbes and its chemistry, compounds and processes that sustain life at the surface. It represents the largest living space on our planet and the most diverse and the most ancient. It has been there, patient and dark, and full of extraordinary life for hundreds of millions of years. It deserves our attention, our patience, our care, not because it is beautiful, though it is, in a way that no photograph has ever fully captured, not because it is useful, though it is, in ways that touch every aspect of our existence, but because it is alive, because the life within it is real and ancient and irreplaceable, because the cold water coral that took 500 years to grow, and the glass sponge that took 300 years, and the polymetallic nodule that took 10 million years, are all, in their own way, extraordinary achievements of time and chemistry and biology, as worthy of our respect as any cathedral or library or work of art that human civilization has produced. The deep ocean is the oldest and largest and most unexplored part of our living planet. And it is asking very quietly, in the language of cold water and slow currents and ancient sediment, for us to be careful, to be patient, to know before we act, to understand before we change. Let that request settle into you now, gently, as you rest. The deep ocean is very far below, patient and dark and full of quiet life. It has been waiting for billions of years. It can wait a little longer, and so can you. You have nowhere to be tonight, nothing that cannot wait. Only this quiet, only this dark, only the long, slow drift of your breath, settling like marine snow through the peaceful deep of sleep. A blue whale is the largest animal that has ever lived on Earth, larger than any dinosaur, larger than any creature the fossil record has yet revealed from any era of the planet's long biological history. A fully grown blue whale can reach 30 meters in length and weigh 150 tons. Its heart is the size of a small car. Its arteries are wide enough for a child to crawl through. It moves through the ocean with a slow, unhurried majesty, its vast body sustained by the billions of tiny krill it filters from the water each day. Its low calls traveling thousands of kilometers through the Sofar Channel we visited earlier in our journey. And when it dies, something extraordinary begins. Not at the surface, where the whale may float for a time before the gases of decomposition release and the body begins to sink. Not in the upper water column, where scavenging sharks and fish may take some portion of the flesh, but at the end of the long, slow descent, when the great body finally settles onto the cold sediment of the deep seafloor, sometimes a kilometer down, sometimes 2, sometimes 4. Something begins that will continue for decades, something that transforms the death of the largest animal on Earth into one of the richest, most complex, and most long-lasting gifts the deep ocean receives. Scientists call it a whale fall. The term is simple and precise, a whale that has fallen to the deep seafloor. But the biological reality of a whale fall is anything but simple. It is a succession of communities, one following the other, each one building on the work of the last, over a timescale that can stretch to a century or more, sustained by the extraordinary biological wealth stored in the body of the largest creature that ever lived. The first stage begins within hours of the whale reaching the seafloor. Word spreads through the deep ocean the way all important information spreads there, through chemistry. The decomposing whale releases dissolved organic compounds into the water, and these compounds diffuse outward in a slow plume carried by the slight currents of the deep. Animals with sensitive chemical receptors detect the plume from considerable distances and begin moving toward its source. Sleeper sharks, those large, slow-moving predators of the deep, cold water, arrive first in many cases. Deep-sea hagfish, those extraordinary and ancient jawless fish that burrow into carcasses and tie themselves in knots to lever off chunks of flesh. Rattlefish, amphipods in their thousands, swarming over the surface of the body and consuming the softer tissues with extraordinary efficiency. This first stage, the mobile scavenger stage, is dramatic by deep-sea standards. A whale carcass can attract hundreds of individual animals of dozens of species, all feeding simultaneously on the enormous resource that has suddenly appeared in the middle of the food-poor abyssal plain, in a world where a single small fish or a fragment of marine snow represents a meaningful meal. A blue whale carcass represents an almost incomprehensible abundance. 150 tons of flesh, blubber, and organ, all at once, in one place. The mobile scavengers are thorough and efficient. Within months, sometimes within weeks for a smaller whale, the soft tissue is largely consumed. The sharks and hagfish and fish move on, following the chemical gradients of other resources elsewhere in the dark ocean. The carcass that remains is very different from the one that arrived. What is left is the skeleton, enormous and pale, lying in a depression in the sediment, surrounded by a zone of enriched organic material, where the decomposition fluids have soaked into the seafloor below. And now the second stage begins. The enrichment opportunist stage brings a different community to the whale skeleton. Polychaete worms arrive in enormous numbers, colonizing the bones and the enriched sediment around them. Small crustaceans, gastropod snails grazing on the bacteria that have begun to grow on every surface. Some of these organisms are generalists, found throughout the deep seafloor, attracted by the unusual concentration of organic material. Others are specialists, animals that are found almost exclusively at whale falls, having evolved specifically to exploit this particular and unusual resource. The bones of the skeleton become densely covered with a living carpet of worms and crustaceans and mollusks. The sediment immediately around them, worked and reworked by the feeding activity of thousands of small animals. It is in this second stage that one of the most remarkable animals in the deep ocean makes its appearance. Ostax is a genus of worms discovered only in 2004, when scientists examining a whale skeleton in Monterey Canyon found it encrusted with animals unlike anything previously known. They called them zombie worms or bone-eating worms, names that capture something of their extraordinary biology. An O-stax worm has no mouth. It has no digestive system of any kind. It has no eyes, no legs, no gut. What it has is a pair of feathery plumes extending into the water above, serving as gills, and a system of green, root-like extensions that penetrate downward into the substance of the whale bone itself. Through these roots, O-stax secretes acid that dissolves the bone mineral, and within the roots, symbiotic bacteria digest the fats and oils stored within the bone matrix. The bacterial partners convert those fats into nutrients the worm can absorb through its roots. It is a partnership of the same intimate kind we have seen before in this journey. The tube worm and its chemosynthetic bacteria, the mussel and its methane-oxidizing passengers. O-stax has taken the fundamental deep ocean strategy of bacterial partnership and applied it to one of the most unusual food sources imaginable, the lipid-rich interior of a whale bone. O-stax worms are not solitary. They colonize whale bones in dense mats. Their feathery red or white plumes covering the surface of every accessible bone. Their roots penetrating through the outer layers and into the marrow within. And their presence transforms the bones themselves by boring through the outer surface of the bone. The O-stax worms increase its structural complexity, creating networks of tiny tunnels and channels that other animals colonize in turn. Bones with dense O-stax populations support significantly more species and significantly more individuals than bones without them. The zombie worm is an ecosystem engineer, using the whale skeleton as raw material and producing from it a habitat far richer and more diverse than the bare bone would otherwise support, as the O-stax worms and the enrichment opportunists work through the organic material in and around the bones. The third and longest stage of whale fall succession begins to develop. The sulfophilic stage takes its name from sulfur, as bacteria decompose the fats within the whale bones. They produce hydrogen sulfide as a byproduct. This is the same compound that fuels the chemosynthetic bacteria cold seeps and the hydrothermal vents, and in the sulfide-enriched environment around a decomposing whale skeleton. The same kind of chemosynthetic community that characterizes those habitats begins to establish itself. Mats of chemosynthetic bacteria spread across the whale bones and the immediately surrounding sediment. Chemosynthetic mussels, those Bathymodiolus relatives we met at the cold seeps, arrive and establish colonies on the bones, hosting their bacterial partners within their gill tissue and drawing sustenance from the sulfide rising from the decomposing lipids within. Polychaete tube worms colonize the skeleton. The whale fall, in its sulfophilic stage, comes to resemble in miniature the cold seep ecosystems we visited. A small, localized island of chemosynthetic life in the surrounding abyssal plain. This stage can last for decades. A large blue whale with its enormous skeleton and its enormous lipid reserves stored within the bones can sustain a sulfophilic community for 50 years or more. For half a century, the bones of a single whale can power a chemosynthetic ecosystem, supporting hundreds of species and thousands of individual animals. In the cold dark at the bottom of the ocean, scientists estimate that at any given moment there are around 690,000 whale carcasses and skeletons on the seafloor of the world's oceans in various stages of succession. 690,000 individual whale falls scattered across the deep seafloor, each one a local oasis of life, each one in a different stage of its long ecological succession, each one supporting its own unique community in the total darkness of the deep ocean. These whale falls are not randomly distributed. They tend to occur along the migration routes of the great whales, in the areas of the deep ocean below the feeding grounds, where the whales spend their summers, consuming enormous quantities of krill and small fish. Each whale that dies and sinks to the deep is, in a sense, returning to the deep ocean a portion of the productivity that was brought up from it, closing a loop of organic material that flows from the surface to the deep and back to the surface across cycles of generations. The final stage, the reef stage, occurs when the skeleton has been reduced to its mineral components, the lipids consumed, the chemosynthetic community fading as the sulfide source is exhausted. What remains is a hard calcium carbonate structure on the seafloor, providing a substrate for the filter feeders and suspension feeders that colonize hard surfaces. Sponges, bryozoans, crinoids, the skeleton of the whale becomes, in its last stage, a small reef, providing habitat not through its chemistry, but through its physical structure, just as a shipwreck does, giving the animals that need hard surfaces something to anchor themselves to in the soft sediment of the abyssal plain. The whole succession, from the arrival of the mobile scavengers in the first hours to the final reef stage decades later, is a story of extraordinary generosity. The whale gives everything. Its flesh feeds the scavengers. Its enriched sediment feeds the opportunists. Its bones feed the O-Stax worms and the sulfophilic bacteria and the chemosynthetic mussels. Its mineral skeleton feeds the suspension feeders. Not a gram of the enormous body is wasted. Every molecule of organic material is processed, consumed, converted, and recycled by the succession of communities that follow one another through the long years of the whale fall's existence. It is the deep ocean's version of something we know from the surface world. The fallen tree in the forest that becomes habitat for mosses and insects and fungi over decades. The body of any creature returning to the soil from which it came, feeding the organisms that will eventually feed the organisms that will eventually feed another tree. But in the deep ocean, the scale is different. The time scales are longer. The communities are stranger and more specialized. And the gift of a single great whale sustains a world of life in the cold dark for longer than most human endeavors last. There is something very peaceful in that, a life as large as the blue whales, and a death as generous. Every part of it used, nothing wasted. The chemistry of that vast body passing slowly through the deep ocean's community becomes becoming part of everything it touches. Rest with that thought now. The great whale, somewhere in the dark below, becoming the deep, feeding the deep, held by the deep, and the patient succession continuing, stage by stage, in the cold and the silence, as it always has. There is a particular kind of knowledge that only comes from going somewhere no one has been before. Not the knowledge you find in libraries or derive from equations or infer from careful reasoning at a desk. The knowledge that comes from arrival, from the moment when the lights of a submersible illuminate something in the dark that no human eye has ever seen, and everything you thought you knew about that world has to make room for something new. The deep ocean has given us many such moments, and the lessons those moments carry extend far beyond marine biology, far beyond oceanography, far beyond any single scientific discipline. They reach into the deepest questions we ask about life, about the planet, about ourselves, and about the nature of the unknown. Let us gather some of those lessons now, quietly, and hold them gently in the mind before we rest. The first and perhaps the most profound lesson the deep ocean has taught us is that life is more resilient, more inventive, and more far-reaching than we imagined. Before the 1970s, the scientific consensus was clear and confident. Life required sunlight. Without photosynthesis, without the conversion of solar energy into organic matter by plants and algae, no complex community of organisms could exist. The deep ocean, beyond the reach of sunlight, was therefore largely barren. A cold, dark, simple place, interesting geologically perhaps, but biologically marginal. The hydrothermal vent communities, discovered in 1977, demolished that consensus in a single afternoon. They showed that life could build rich, complex, diverse ecosystems on chemical energy alone, entirely independent of the sun, that the foundation of a food chain did not have to be photosynthesis. That darkness was not a barrier to biological abundance. That the rules we thought governed the distribution of life were not rules at all, but assumptions assumptions deserve to be tested. Since then, the deep ocean has continued to revise our understanding of the limits of life. Microbes living in sediment 101.5 million years old, bacteria dividing once every 10,000 years, sustaining themselves on the faintest possible traces of ancient organic material. Snailfish living at depths of more than 8,000 meters, in pressure that should crush any complex animal. Pompeii worms tolerating temperatures that would kill any other multicellular organism. The deep ocean has moved the boundaries of what we thought possible so far, and so often that most deep-sea biologists now approach the question of life's limits with humility rather than certainty. The lesson is not merely biological, it is philosophical. We had drawn a circle around the conditions that life requires, and the deep ocean stepped outside that circle again and again, with a calm indifference to our expectations. It suggests that wherever in the universe the conditions exist for chemistry to proceed, for energy gradients to be maintained, for water to remain liquid, the possibility of life cannot be ruled out. The deep ocean has made the universe seem more alive with possibility. The second lesson is about time. The deep ocean operates on timescales so far beyond human experience that engagement with it requires a fundamental shift in perspective. A cold water coral reef growing at less than 1 centimeter per year, reaching a height of tens of meters over thousands of years. Polymetallic nodules accumulating at a rate of a few millimeters every million years. Microbes in the sediment that have been metabolizing since the age of the dinosaurs. The thermohaline circulation carrying water on a journey that takes roughly 1,000 years to complete a single cycle around the world's oceans. These timescales are not merely large numbers. They represent a different quality of existence, a different relationship between an organism and its environment. The deep ocean has been teaching us consistently and insistently that our human timescales, the years and decades and centuries that frame our history and our planning, are not the timescales on which the planet operates. The planet operates on the timescales of the deep ocean, on the timescales of geological processes and biological successions and microbial metabolisms measured in millennia. Understanding this is not depressing. It is liberating. It places our brief, vivid lives in the context of something vast and patient and enduring. We are not the measure of all things. We are a recent arrival in a world that has been slowly and patiently building itself for 4 billion years. The deep ocean, more than almost anything else in our experience, makes that viscerally, quietly, undeniably clear. The third lesson is about connection. The deep ocean looks, from our perspective, utterly separate from the surface world, unreachable, alien, governed by different physics and different biology and different chemistry. And yet we have seen again and again throughout this journey that the deep ocean and the surface world are intimately and inseparably connected. The marine snow that feeds the deep begins as phytoplankton at the surface. The thermohaline circulation that regulates global climate is driven by the sinking of cold, dense surface water. The carbon dioxide we emit into the atmosphere dissolves at the ocean surface and is carried to the deep by the biological and physical pumps. The nutrients that support the vast productivity of the sunlit ocean are supplied largely by the upwelling of deep water that has spent decades or centuries accumulating them in the dark below. The enzyme that makes modern medicine's most powerful diagnostic and research tools possible was found in a microorganism from a deep-sea thermal environment. Nothing in the deep ocean is truly separate from the surface. Everything circulates. Everything connects. The boundary between the shallow and the deep, between the sunlit and the dark, between the world we inhabit and the world we have barely begun to explore, is a boundary of perception, not of reality. The ocean is one body of water. The planet is one system. And the deep ocean is not the far end of that system. It is the foundation of it. The fourth lesson is about humility. We have been mapping the deep ocean seriously for less than a century. We have visited the deepest point on Earth fewer times than humans have walked on the moon. We have described, at generous estimates, perhaps 10 or 20% of the species that live in the deep ocean. We have sampled a tiny fraction of 1% of the deep seafloor directly. We have been monitoring the chemistry and temperature and biology of the deep ocean systematically for only a few decades. A blink of an eye in the context of the processes we are trying to understand, and in that brief, partial, fragmentary engagement with the deep ocean, we have already made discoveries that changed the course of multiple scientific disciplines, overturned fundamental assumptions about the nature of life, found new species by the hundreds every year, and revealed a world of such complexity and beauty and strangeness that it has stretched the imagination of every scientist who has encountered it. What is still down there in the 70 or so percent of the deep seafloor we have never mapped. In the vast majority of deep ocean species we have never described. In the microbial metabolisms we have barely begun to characterize. In the ecosystems we have never surveyed. The honest answer is that we do not know. We do not know what we do not know. And the deep ocean has taught us, repeatedly and reliably, that what we do not know is always larger, stranger, and more wonderful than what we imagined. The fifth lesson is about wonder. This one is harder to express in the language of science, but it is no less real for that. There is a quality to the deep ocean that goes beyond the informational, beyond the useful, beyond the economically valuable or the scientifically significant. It is the quality of sheer, quiet, astonishing existence. The fact that in the cold dark at the bottom of the Mariana Trench, small pale snailfish are going about their lives, feeding and moving and existing in conditions that everything in our intuitive understanding of the world suggests should be impossible. The fact that a siphonophore 40 meters long drifts through the midnight zone right now, its colony of specialized individuals cooperating with an intimacy that blurs the boundary between one and many. The fact that somewhere on the abyssal plain, a stalked crinoid has been standing in the same slow current for 100 years, filtering marine snow with feathery arms that look almost exactly like the feathery arms of its ancestors from 450 million years ago. These facts do not need to be useful to matter. They do not need to have medical applications or climate implications or economic value. They matter because they are true, because they are part of the living world we share, because the universe has arranged itself through 4 billion years of chemistry and evolution and geological upheaval into forms of such improbable and extraordinary beauty that the only appropriate response when you encounter them is a kind of quiet, grateful astonishment. The deep ocean has given us that astonishment again and again to everyone who has gone there to look. And through the films and the photographs and the scientific papers and the descriptions that have found their way back to the surface world, it has offered some fraction of that astonishment to everyone who has paid attention. The sixth and final lesson is the simplest and perhaps the most important. We do not know our own planet. Most of the surface of the earth is covered by water. Most of that water is deep. Most of the deep is unexplored. The largest habitat on Earth, the largest living space, the oldest continuous environment, the place where life itself may have begun, the system that regulates the climate and chemistry of the surface world, the refuge of the most ancient lineages and the most extreme biologies, is still, in the most fundamental sense, unknown to us. We live on a planet whose largest feature we have barely visited, whose most numerous inhabitants we have barely named, whose most important climate-regulating processes we have only recently begun to understand, whose most ancient communities we have encountered only in glimpses, through small viewports, in brief dives, in scattered samples from a vast and largely uncharted world. That is not a failure. It is an invitation. The deep ocean is still there, as it has always been, patient and dark, and full of extraordinary life, waiting to be known, not demanding our attention, requiring our understanding to continue its ancient work, but offering to anyone willing to go slowly and look carefully and be genuinely surprised, a world of such depth and strangeness and beauty that a lifetime of exploration would barely scratch its surface. And tonight, without leaving this bed, without descending a single meter, you have been there. You have drifted through the twilight zone and the midnight dark. You have stood beside the hydrothermal vents and felt the warm water rising. You have watched the marine snow falling through the black water. You have heard the so far channel-carrying whale song across an ocean. You have rested on the soft sediment of the abyssal plain, while stalked crinoids filtered the slow current above you. You have been to the deep ocean tonight, and the deep ocean, in its quiet and patient way, has been here with you. It is still here now, vast and dark and full of life below everything, holding the world in balance, turning its ancient chemistry, and completely, deeply, perfectly at rest, as you are now, as you will be deeper and deeper through all the quiet hours ahead. You have been to the bottom of the world tonight, not in any dramatic way, not with noise or effort or urgency, but quietly, in the way that the best journeys happen, drifting down through the water with the ease of a snowflake, settling through the dark layers one by one, carried by the gentle pull of curiosity and the even gentler pull of sleep. And what a world it was. Think back now, very softly, not with any effort, just letting the images rise and fall like the slow pulse of a siphonophore in deep water. The surface of the ocean, bright and restless, where the phytoplankton drift in their millions, and the marine snow begins. Each tiny particle setting off on its long journey downward, carrying a small cargo of carbon and life toward the deep, patient from the very beginning. The twilight zone, where the last blue light filters through the water in long, wavering columns, and the hatchetfish wears its coat of light to disappear against the glow from above, where the giant squid moves unseen and the lanternfish rise each evening toward the surface in the largest daily migration on Earth. The midnight zone, where the light goes out entirely, and bioluminescence becomes the only illumination. Blue flickers in the dark, the slow pulse of a jellyfish, the lure of the anglerfish, glowing with its passenger of light-producing bacteria, drawing prey toward a darkness deeper than the dark around it, the abyssal plain, soft and pale and impossibly still. The sea cucumbers moving slowly across the sediment, sweeping it into their mouths. The stalked crinoids standing in the slight current, their feathery arms extended, filtering the last traces of marine snow from the water that has fallen so far to reach them, the glass sponges with their silica skeletons, carrying within them the principles of fiber optics, growing at the pace of years and decades. The hydrothermal vents, where black water rises in columns from the seafloor, and the giant tube worms stand in their thickets, red plumes waving, nourished entirely by the bacteria within their own bodies, a world that needs no sun, a world that proved, to the astonishment of every scientist who first saw it, that life does not require light to exist, only chemistry, only the patient energy of the earth itself, rising from below, the cold seeps, breathing their slow methane through the sediment, feeding their pale bacterial mats, gathering their mussels and their tube worms and building, over centuries, the carbonate rock that cold water corals will one day call home, each community creating the conditions for the next, in a succession so slow that no individual creature within it can perceive it from beginning to end. The soft-bodied drifters of the open water, the comb jellies with their rainbow cilia, the siphonophores, those extraordinary colonies that are both one animal and many, trailing their 40-meter bodies through the cold dark, patient and slow and alive in ways that make the word alive feel newly interesting. The extraordinary fish, with their telescoping eyes and their hinged jaws and their expandable stomachs and their glowing bellies and their transparent skulls, each one a masterwork of evolutionary patience, shaped over millions of generations into exactly what it needs to be, and nothing more, in the cold and the dark and the pressure, the microbes, small numerous of all, running their ancient chemistry in the deep sediment, eating material centuries old, dividing once every 10,000 years, persisting in conditions that should be, by every prior understanding, incompatible with life, and yet there and alive, and turning the chemistry of the planet in their slow and patient hands. The Sofar Channel, threading its acoustic highway through the ocean at mid-depth, carrying the long, low calls of blue whales across entire ocean basins, a sound below human hearing, a vibration felt rather than heard, the planet communicating with itself across distances that dwarf any other signal our world produces, the seafloor spreading at the mid-ocean ridge, millimeter by millimeter, year by year, making new rock from the molten interior of the earth, pushing the plates apart, widening the oceans, building the seamounts and the trenches and the ridges and the plains across which all tonight's creatures make their quiet lives, the shipwrecks resting in the dark, becoming reefs, becoming habitats, slowly being consumed by metal-eating bacteria and colonized by cold water corals, their human stories preserved in cold salt water, while the deep ocean makes something new from what remains, the microbes and the chemistry and the biological pump, moving carbon and heat and nutrients through the ocean in cycles that regulate the climate of the entire planet, absorbing the consequences of a warming world with quiet, enormous, uncomplaining patience and all the unnamed things, all the species still unknown to science, living their ancient lives in the cold dark, carrying within their bodies biology that no human has ever studied or described, all the discoveries still waiting in the deep, the new species, the new behaviors, the new ecosystems, the new chemical processes, the new wonders. All of it right now, continuing. The deep ocean does not pause when we stop paying attention. It does not wait for us to return. It continues its ancient, patient work, regardless of whether anyone is watching. The marine snow is falling right now. The crinoids are filtering right now. The bacteria in the deep sediment are turning their ancient food very slowly right now. The thermohaline circulation is moving cold water toward the tropics right now. The mid-ocean ridge is making new rock right now. All of it, all of it, all of it, continuing in the dark and the cold and the silence, as it has continued for hundreds of millions of years, and as it will continue for hundreds of millions more. And you are on the surface of that ancient, restless, living world, floating, held up by the same ocean that descends below you. Through all those layers we visited tonight, the sunlit layer and the twilight layer and the midnight zone and the abyss and the Hydrothermal trenches at the very bottom of the world, all of them below you, all of them connected to you, all of them part of the same water, the same chemistry, the same planetary system that makes your life possible. You do not need to hold any of it in your mind right now. You do not need to remember any of the names, the depths, the creatures, the processes. You only need to rest. The ocean will take care of the rest. It always has. Long before there were human beings to think about it, or wonder at it, or name its creatures, the deep ocean was doing what it does, and long after, it will continue. Patient and dark, and full of quiet life. The largest and least known and most ancient part of our living world, going about its work with a thoroughness and a dedication that makes all human effort seem brief and small, and in the best possible way, unnecessary. You are not needed tonight. Nothing is required of you. No problem needs your attention. No question needs your answer. No task waits for you in this hour. There is only the dark and the quiet and the long, slow drift of your breath settling through the peaceful layers of sleep like a single particle of marine snow, very slowly, very gently, down through the blue, down through the dark, down through the cold and the still and the ancient deep, all the way down to rest. This has been Sleepy Facts with Justin. Thank you for spending this night in the deep ocean. Sleep well